So the implementation should be effective.
Hello everyone, in this video,
The volume is pretty high, right?
Yeah, but we're gonna switch it to, that's coming from the projector, so we're gonna switch it to this thing, I think.
That speaker.
It's probably a bit better of a speaker. We'll try that.
PV panel and 4 fixed bracket and 2 brackets.
That's more clear.
Yeah.
On the fixed bracket, there are holes that I can mark the number from number 1 to number 9,
Something like that.
and the other bracket I also mark 1.5 to number 9. So to set the tilt angle at 10 degrees, I use the 2 bracket mounted from 1.5 on this bracket to number 8 on the other bracket.
All right, we won't give away the whole thing.
All right.
We need another treadmill in here. The pace. The pace.
It's not hard, man. You don't have it. I don't know. You don't need to be focused on maybe with friends. Which is a secret thing. However, we will do this is.
You're good at speaking.
You gotta think about something else.
Yeah. No, you're good.
Okay.
Our projects are
My presentation just stopped coughing. Stop using the phone.
Put great channel legends to it.
Great channel legends.
The insult. Last time you gave him a rifle. Last time you gave him a rifle.
One. I will show you.
You can send me
No, that's okay.
How's it going? Good, yeah. Pretty good. It's been a few years, yeah. Yeah. Yeah, still there, still busy.
What is the option?
Yeah. The last year, I've been supervisor.
Still work or did it die on the roof? Does the fucking gen still work?
Let's say it's close.
Yeah.
It died on the way here. They got stacked inside the car.
5 or 6 years ago, I moved from like field technologist.
So you mean that you want to know how to open this one?
Not that way.
This one next. How can I open it? Just apply.
Yeah, sort of. A lot of our ATM training stuff.
Yeah, I need open very Yeah.
But we sold our labs
Let's see.
last year. So we still
Just apply,
use
right?
part of the building for training, but they're looking
Analysis.
at
Yeah.
new location. Like, look at.
It's the file when I.
Violently.
Yeah, just so.
Like the
Yeah.
It'll be okay.
Yeah. So I need to check the timer because the timer when I start it, when I open it restart the timer. That's why I need to use this one. Check I remember. Because just see it. Yeah, I can remember because my project work with the numbers. But in the past
I'm doing your presentation.
the first page, I need to remember.
Somewhere between.
Yeah, all the page, all the numbers.
We still have to send things. It'll be easy to
When
access from there.
Oh, this guy.
They still might even go
Yeah,
to
look
the
to you too.
all of our ATM.
I was asking.
Yeah, this morning we done.
Yeah. Having some
Instructors.
Try our
Stuff
best.
like instrument systems and stuff like that. We have all that.
it shouldn't be hard now, just exactly what set out.
But
My project work numbers. So Yeah.
And CPMs.
Yeah.
Full life, field, and just shows. And how.
5, 6, 6. And when one is testing yourself, because my technique data analysis.
Or.
But the other guys, they are protect electronics, so it makes like a schematic wiring there. For me, testing. So I will talk more about testing than the other.
We did,
Because my system is very simple. Just a PV panel and one lock and another shunt resistor. That's it. Just connect.
okay, whatever it was. So I think the students were.
Good luck.
All.
We see you again. Before lunch.
So at least they could have some. No, but.
Oh,
But at least they could. Yeah, yeah. I guess.
we got a class now.
Yeah, it's crazy. So I've got our new VP. Yeah, good time, and it was a good time, but he came in at a bad time, and then.
Yeah, I also got the shit.
He didn't have the best
I
name.
think it's more from the
He's very
8
focused.
pizza pockets than I did.
Maybe also.
Yeah, I didn't.
That was the first time.
No, but it doesn't mean my body always likes it.
I mean,
Can't doesn't mean I
should.
should.
Cool stuff. I'm like, well, it's pretty cool. Yeah. But most of it's older than me. Yeah.
They knew you were coming and you're like,
Yeah. Like our radars, on cards. So we, like,
that's clap.
they.
Except for super.
And we took that to a third party and got it.
So,
260.
so. Oh no, yesterday I didn't ask you about what was it? I'm like, get on the level, SMH. New Zealand.
Yeah, we've done that before, they bought.
Oh dear. It is clean the DC voltage in the butt crash for any more
It's sports, yeah. And then, like a lot of all of our engineers. We should get. Just 2%.
Yeah, that would be good.
Just sit in the back.
Oh, gosh.
No, I did, yeah. But I probably in the back.
You're welcome.
Oh, thank you, yeah.
I missed them back in high school. I worked in high school, so it's not this is sometimes that I know.
Okay. Good morning, everyone. Welcome to day 3 of our Senior Project Symposium. This morning, starting out the morning for us is Chung Fong, and he's going to be presenting on his analysis project of optimum tilt angle versus additional panels.
Yeah, thank you.
Yeah.
Good morning, instructor, and good morning, everyone. Today, I would like to present my project about the optimum tilt angle and additional panel analysis. I will go through the main content for the topic. The first one, I will answer the why PV tilt angle analysis is necessary for my project, and the second one, how I set up the data collection system, and the next one is the site assessment and method of data analysis, and the main part is the testing and result, and finally we come to the conclusion. So why PV tilt angle analysis is necessary for my project? We know that the solar panel will generate most power when its surface is at the right angle to the sun's ray. But in reality, it does not always happen because the sun moves across the sky throughout the day, and its angle always changes when the season is changed. If so, how to maximize the power generation of a solar power system based on this understanding is a challenge. And some people think that they can adjust the tilt angle to maximize the power generation, but the others, they think that just adding more power, more PV panel to maximize the power generation. So for my project, I have to do the PV tilt angle analysis to answer this question. This is my block diagram. In my project, I have to set up 2 identical systems to collect the data. One system, we have one PV panel, and the one system have a one PV2 angle. PV panel, and it's set at a fixed optimum tilt angle. And the other system also have one PV panel. The tilt angle will be adjusted from 10 degrees to 90 degrees. The panel will collect the energy from the sunlight and convert to electricity, and it will go to the dummy lock and some resistor. The data acquisition, I call it DAC in this project, will monitor the voltage across the dummy lock and the voltage across the sum resistor. The DAC will collect the real-time data and it will export to the computer. The computer already installed the Windows software, and it will run the real-time data, get the data from the DAC, and then at the end of the day, it will generate a waveform, and we use the waveform to export the data to Excel. Then from the Excel, we use the method of data analysis to analyze the data, get information out of the data, then we make the conclusion to answer the question. In the meantime, I also get the cost survey from some solar installer in Moncton to get the cost of installing the adjustable tilt angle or add more panels. The next one, how I connect the system to do the data collection. The PV panel will connect to the dummy lot. Sorry. The PV panel will connect with the dummy lot and the sum resistor. These two connect in series, and I use the wire 10 gauge wire connect from panel to the dummy lot and the shunt resistor. And the shunt resistor and the dummy lot and the dot in my project, I put in an enclosure. In the enclosure, I reduce the gauge of the wire to 16 because I need to plug in the channel on the dot. And on the dot, there's a port to export the data to laptop with the USB connection. On the laptop already installed with that. So how I set up the data setting on the data acquisition device. The model name of my data acquisition device is DI245, and it can measure the voltage and the temperature. In my project, I use the input type voltage. As I mentioned, I have two identical systems. One system with one single panel, and one system I fixed at the optimum tilt angle at 45. And I use channel 1 and channel 2 on the data acquisition to monitor the voltage. The second system, I adjust the tilt angle on the PV panel, and I use the channel 3 and channel 4. Channel 1 and channel 3 on the dot, we measure the voltage across the dummy load on two systems, and I set the range plus minus 25 volt. For channel 2 and channel 4, I measure the voltage across the shunt resistor, and I set the range 1 plus minus 1 volt. The sample rate, I set one sample collected in 100 seconds. For the adjustable tilt angle system, I use the adjustable mounting bracket. It can be adjusted from 10 degrees to 90 degrees. For the site location, this is the location that I put my panel for data collection. And in this site assessment, I do the shading analysis. I use the solar pathfinder to check the site percentage in the month that I do the data collection from March to May. And on the picture, you can see that the area around there's no any big trees or high building for the south-facing direction of the panels. And this is the installation data for the location. I get the installation data in Moncton on red screen, and the data collect from February to May at different tilt angle from horizontal to 90 degrees. And you can see on the table from 20 degree tilt angle to 60 degree tilt angle, the daily solar variation on average are almost close. So my optimum tilt angle is 45. So I think it's correct choice in this case. This is just a theoretical data that I get from red screen. So now we go to the actual result. This is my method of data analysis. Because after we have data, so we need to analyze the data to get the information to answer the question. So the first method I use is Chapter switch. This method, I calculate the power difference between optimum tilt angle 45 and adjustable tilt angle. I calculate the area between two power generation curve, and I sum up all the area to get the total energy difference between two tilt angles, and then divide it by the total hour of the data collection, and I get the average power gain or loss depend on different tilt angle. The second method is the normalization. Because my system doesn't have the MPPT, so I could not get the maximum power. My power generation is around 20 watt, more or less. So that's why I have to use the normalization to scale up the power to power rating of the panel, to calculate the number of panels in one specific project to do the comparison. And now the main part is testing the result. Firstly, I would like to summarize how different during the data collection. Over the period of the data collection, I change the tilt angle from 10 degrees to 90 degrees. And at each tilt angle, I do data collection in 6 to 8 days. And in each day, around from 5 hours to 10 hours, depending on the weather condition. Then I use the first method to get the average power difference. But actually, because the panel, they only have the tolerance from manufacturing, so that's why I have to do the calibration between panels at different tilt angles to get the variance. And after I get the variance at different tilt angles, I compensate for the average power to get the adjusted power. This is actual different power difference between two tilt angles. Now I'll come to the first tilt angle at 10 degrees. At 10 degrees, because I do data collection for two systems at the same time, and this is between 10 degree tilt angle and 45 degree tilt angle. You can see that in the noon time, around 12 p.m. to 4 p.m. or 5 p.m., the power generation from 10 degree tilt angle seems a little bit more than 45 degree tilt angle, but just a little, not much. But the beginning of the day and the end of the day, you can see that the power generation from 45 degree still higher than 10 degree tilt angle. And this is my table for comparison. As I mentioned before, because my maximum calculated power not high, it's around more or less 20. So I need to do the normalization to scale up to the power rating of the panel. So yeah, and then I get the power loss, power gain from 10 degree to 45 degree is 6.83%. Then I choose one typical annual solar generation project, which has about 10,000 kilowatt hour, and then I can calculate to the system side, get 8.75 kilowatt. Then I can get the number of panels for 45 degree tilt angle is 88, and for the system with 10 degree tilt angle, the number of panels needs is 94. So the extra panel that the 10 degree tilt angle need to be added to get the same annual solar duration as the 45 degree tilt angle is 6 panels, equivalent to 600 watt because I used 100 watt panel. So this is cost comparison. For cost comparison, I do the cost comparison between the option to add more panel and the option to adjust the tilt angle in two scenarios. The first scenario is the roof, for the roof mount. The second scenario is the ground mount. The first scenario, so I got a quotation from a solar installer in Moncton, and they tell me that the average cost for one extra panel is around 1,000 more or less. So that's why I divide it by 100 and get from 8 to 12. This is just estimate. But for the adjustable roof mount, the cost per installed watt is go up to 43. It's because for the roof mount, you need to change on the rack for existing installation to the adjustable racking, and for the roof mount, the maximum number of panels that can install per rack is about 4 or 6 panels. So that's why if we have 88 panels, we need around 22 panels actually 22 set. And one set costs you 1,069 before tax. And you plus the installation cost, because the cost 1,069 only the cost for the setup rack, not including installation. So that means I need to plus the installation cost and divide it by 600 watt. I get the 43 watt. In the second scenario, for the ground mount, the option of adding more panel costs you $6.85 to $30.70. For the fixed ground mount, so I base on the cost of the rack on the ground. It costs you depend on the number of panels you want to carry per rack. So in this case, we have 6 panels. I choose the size for 6 panels. So it costs about almost 2,000. And plus the cost of installation. So and divided by 600 watt, you get a minimum cost for installed watt is $6.85. And for the maximum, because I also get information from the other supplier, they mentioned that when they do the installation, the minimum cost that for installation is if the capacity is less than from 10 kilowatt and less than, they charge you a fixed cost $6,000 plus the installation cost. So in this case, I choose this number at the maximum and divide it by 600. For the adjustable ground mount, I choose the maximum number. I choose the racking with the maximum panel. It can carry 46 panels on one rack, and in this case we have 88. I choose. We have to pick up two. We have to use 2 sets, and 1 set costs you about $8,600 just for the racking. And then plus the installation cost divided by 600, you get $32.33. So now I go to the 20-degree triangle. For the 20-degree triangle, so the power generation between 20-degree triangle and 45-degree triangle are almost very close. So I do the calculation based on the data collection for over the period for the 20-degree triangle, and I get the final number is for power gain is 0.82%. So it's same as the information I got from the graph. Yeah, between the calculation and the graph. The same thing. The extra panel for 20-degree triangle is only one panel, because you see the power generation almost same. So the extra panel is very small, only one. Equivalent extra power also 100 watt. And the cost of adding more panel with the roof mount is $8 from $8 to $12. But for the adjustable roof mount, because the number of extra watt is reduced, so that's why the cost per watt is increased. The same thing with the ground mount. So the cost for the fixed ground mount, I can write from $22 to $63, but for the adjustable ground mount, it go up to $175. With a 30-degree triangle, so for a 30-degree triangle, you see that the power generation from the 30-degree triangle is a bit higher than the 45, but not much. And for a comparison, the power gain after calculation, I got the power from generation from 30-degree triangle is actually higher than the 45-degree triangle. This one because I use the power generation from 45-degree triangle minus 30-degree triangle, so that's why it comes to negative number. In this case, because at a 30-degree triangle, the power generation generate more than the 45-degree triangle, so we have no reason to add more panel or just the triangle. So I don't do the cost comparison for this case. At the 40-degree triangle, so the power generation between 45 and 40, sorry, between my mistake, should be 40. The graph is correct, but the title I put incorrect. It should be 40. So they are both almost close. And based on calculation, it's only 0.96%. And the same thing as 20-degree triangle, the extra panel in this case for the 40-degree triangle is only one panel. And extra power only 100. So the cost now, the cost is same. So for the adjustable triangle option, it's always higher than the adding more panel. Now we go to the 50-degree triangle. With the 50-degree triangle, the power difference also a little bit between 45-degree triangle and the 50-degree triangle. So for the 50-degree triangle, extra panel also is one panel only, and the cost almost same as the 40 and 20 degree. At 61, the power generation from the 45-degree triangle is higher than 60-degree triangle, 3%, 3.41%, and the extra panel for 61-degree triangle to get the same annual solar generation at the 45-degree triangle system with 3 panels. The extra watt is 300 watt. For the cost comparison, so now because the extra watt increase, so the cost per installed watt for adjustable roof mount and adjustable ground mount reduced a bit to 82 for roof mount and 61 for ground mount. And this is for 68-degree triangle. Based on my calculations, the power gain from 68 to 45-degree triangle is 7.5%, and the extra panel for 68-degree triangle is 7 panel. Is equivalent to 700 watt, and the cost per installed watt for adjustable roof mount is also high, still $37 per watt, and for adjustable ground mount is $28, 27. At the 81-degree triangle, you see that the gap between 45-degree triangle and 81-degree triangle is a bit higher. And based on my calculation, it's go up to 70.68%. That means for the 81-degree triangle system, if you want to get the same annual solar generation at 45, you need to install more 19 panels. It's equivalent to 1.9 kilowatt. And the cost now for adjustable roof mount and adjustable ground mount is reduced significantly. So but it's still higher than the cost of the adding more panel for the fixed with the fixed roof mount or the fixed ground mount. And this is a 90-degree triangle. With a 90-degree triangle, you can see also the big gap between 45-degree triangle and 90-degree triangle. This is 45-degree triangle and this is 90-degree triangle. And for the cost comparison, for the power gain is also 7.25%, almost same as the 68-degree triangle. And extra panel is 7 and extra watt is 700 watt. For the cost comparison, it's also same as the 68-degree triangle case. So for the fixed ground mount, I did not change because for the roofing, so the cost per watt for adding more panel is still the same. And for adjustable roof mount is $37, and for adjustable ground mount is $28 or $27 per watt extra. And now is my conclusion. So because my project was carried out in Moncton from March 9 to May 16, That means around end of winter to spring. And the panel, I use 100 watt panels. So I come to conclusion based on the data collection and analysis. The power generation between the optimum tilt angle 45 and the other tilt angles from 20 degree tilt angle to 60 degree tilt angle is only less than 5%. The cost of installing adjustable tilt angle is very far from the cost of adding more panel per watt. I think this result same as the data I got from red screen. That means from 20 degree tilt angle to 60 degree tilt angle, the solar radiation is almost same. So that means there's not much difference in power generation between these two angles. With the other tilt angle like 10 degree, 68 and 81 and 90, even the power generation is a bit higher, more than 7%. But the cost of installing adjustable mounting still higher than the cost of adding more panel. For my project that I choose is 10 kilowatt hour or less. Because if we reduce the annual solar generation, that means the extra watt, extra power generated when we change the tilt angle is less, and the cost almost doesn't change so much. So that's why it's still not effective if we change the tilt angle. And the last one is for residential existing power system. The adjustable tilt angle is not a cost-effective solution compared to adding more panel. Yeah. I think this conclusion is valid for Moncton and for the period from end winter to spring. So I think if we have more time for 1 year, so we can get more informative conclusion. Yeah. And this is my reference for the project. So now I will show you my demonstration for tilt angle adjustment and data collection setup.
Hello everyone. In this video, I will show you how I adjust the tilt angle for the PV panel with the adjustable bracket. I have one PV panel and 4 fixed brackets and 2 tilt brackets. On the fixed bracket, there are holes that I can mark the number from number 1 to number 9, and the other bracket also mark 1, 1.5 to number 9. So to set the tilt angle at 10 degree, I use the tilt bracket mounted from 1.5 on this bracket to number 8 on the other bracket. And if I want to increase the tilt angle to 20 degree, I just mount from number 2 to number 8, and so on with the 30 degree and 40 degree as well. So now let's take a look how I adjust the tilt angle to 10 degree. This is the 10 degree tilt angle. For the 10 degree tilt angle, the tilt bracket mounted from 1.5 to number 8. The tilt angle is now 10 degree. For the 30 degree tilt angle, the tilt bracket mounted from number 3 to number 8 on the other bracket. And now the tilt angle is 30 degree. This is a 70 degree tilt angle. For the 70-degree triangle, the two brackets mounted from number 7 and to number 9 on the other bracket. If you want to increase the triangle to 80 or 90, you can move from number 7 to number 8 or number 9. This is 70-degree triangle. And this is the location where I do the data collection for my project. I use two PV panels. One PV panel I set at 45 degree, and the other is right now 70-degree triangle. The reason I put the two panels on the ground for data collection is because it's easy for me to adjust the two angle from 10 degree to 90 degree. The panel on the left side is the panel used for the adjustable two angle, and this panel on the right side is used for the fixed optimum two angle at 45. These two panels are connected to the W lock and shunt resistor with the data acquisition measure the voltage across the W lock and the shunt resistor. They are all put in the enclosure. The enclosure are put in the basement, so the wire go to the basement. After the wire go to the basement, it will be go to the enclosure. In the enclosure there are two W lock and two shunt resistors because I have two systems and one duct. The duct is connected to the laptop by USB cable. On the laptop, I already installed the WinDuct software. So after we finish the connection, we just start the WinDuct. The first step, before we do the data collection, we have to go to the channel setting. As I mentioned, because I have two systems, so one system I use channel 1 and channel 2, and the other system I use channel 3 and channel 4. For channel 1 and channel 3, it measures the voltage across the W lock. The voltage is almost 20 or over 20, so that's why I choose the plus minus 25. So channel 1 is set 25, and channel 2 and channel 4 measure the voltage across the shunt resistor. I set only plus minus 1 because the voltage across the shunt is very small. The channel 3 also same as channel 1. I also use the range plus minus 25. And the last one, channel 4, I use the range plus minus 1 volt. The next step is to set the sample rate. For the sample rate, I choose 0.04 to select the sample in every 100 seconds. And then finally, I go to file and then record the real-time data. So I put the name for the file for the data collected in the day. In the name I put it test May 20 at 70 degree because right now my triangle is 70 degree for the adjustable system. And then I set the recording time. In my project I set the 10 hours per day. And now the system already automatically record the data. So you can see 4 channels. Channel 1 and channel 2 measure the voltage across the W lock. Channel 1 right now is 19.4, nearly 19.5 volt. And channel 2 is 18.4, nearly 18.5 volt. Channel 2 and channel 4 measure the voltage across the shunt. The voltage right now across the shunt is around 8 millivolt. That is the setup for the data collection. This is the end of the video.
I'll start. Sean, can you go on the slide where you compared the angle to 30 degrees? So at 30 degrees, you had more power at 30 degrees versus 45. Why is that?
Because it depends on the days. Some days the sunlight go high, so that's why the triangle, the less triangle is absorb more power. Especially like I mentioned in for the 10-degree triangle. So in the noon time, the 10-degree triangle is absorb more energy from the sunlight than the 45. Yeah, actually it sometimes depends on the weather condition on the day.
You ran your test for 10 hours in a day, right?
Yeah, 10 hours, but actually some days because there's snow or raining, there's no sunlight, so I may cut the hours from 10 hours to 5 hours or 6 hours to 10.
But should not the effect be the same on both
Right,
panels?
the temperature effect
Yes,
or the
so
effect
effect
of the
on both
day is the
panels.
same for both, right? But because one is tilted at 45 versus 30, why are you getting more power on 30 degrees even though your optimal tilt angle is 45?
Actually, first, the power generation between 45 and 30 is not much different, but as I mentioned, because the sunlight when it go high, so the 30-degree triangle, the less triangle, so it absorb more power, more energy from the sunlight.
So why don't we leave it at
But the
30?
gap is only a little bit.
Why don't we just leave it at 30 all year round then?
I think we can, because from 30 to 45, actually, oh sorry, not year round, because my project only lasts in from March, my data collection from March to May, so I can compare them from March to May, so it does not have any difference between 30 or 45. But in the case we want to apply for whole year, so we need to collect the data, more data for
That's what happens in the summer with the sun.
with the sun, I think 30 should be
No, but in the summer, what happens to the sun in the sky?
in the summer. I think the sky will be higher, so that means the less triangle will absorb more
And
energy.
in the winter?
In the winter, so the high triangle, more than 45,
Okay,
will absorb more power.
okay. So you were at what condition there?
Right now, because the weather changed from the winter to the spring, some day I see that more sunlight, very sunny, but some day snow or rainy.
It's got nothing
So
to do with that.
it's hard to explain.
If it's cloudy, that's going to impact both,
Yeah.
so that's not the reason.
Unless you're thinking anyone. Oh,
But actually, it's based on the real data. So yeah, just so the real
But
data.
as you're transitioning from winter to summer, or summer to winter,
Yeah, somewhat.
what angle,
I think from summer to winter, so the tilt angle should be increased. Yeah, in the summer the tilt angle is less, but when it comes to winter,
so when
it
you're in
increase.
spring halfway, you're increasing to from what value to what value, and in the winter you're going from what value to what value. So in the spring, shouldn't you be halfway there?
The spring. Yeah, the spring should be halfway. Yeah, for winter and summer.
Okay, so wouldn't 45 degrees be your halfway point?
Yeah, I think so. Yeah.
That's probably why you can't do this. Maybe it's closer to summer.
Can you show your table again from red screen? That was one of the
Yeah.
initial slides. Did it show the optimal tilt angle
Yes.
per month?
Yes, the optimum tilt angle. For example, for February, it should be 50, and when you go to March, it reduces. Yeah, so say 50. Yeah, so 50 go to April. 63 go back to go to 30. And in May, optimum tilt angle is.
So that test was performed in May, right?
This is not the testing data. This is the.
No, but I'm just referring back to your your other graph, when was that test performed, the 30 degrees versus 45?
The 30 degree,
You can go back and check the date. April.
around April.
Right. Yeah, the table on red screen showed better efficiency at 30 degrees in May, so we're probably close to that. Makes sense. Okay.
That was an interesting discussion.
I think you mentioned that you're using the tag to measure the voltage across the dummy load and across the shunt resistor. So you're doing the same thing?
Yeah, I do the same thing.
So you're measuring the voltage across the shunt and across the dummy load?
Yeah, I measure the voltage. Because the DAP have 4 channels, I use the first 2 channels, measure the voltage across the dummy load and the shunt resistor on for the first system. And the second system, I use the channel 4, channel 3 and channel 4 to measure the voltage across
So
the
you measure in the same quantity this way, like you measure in the same thing?
Yeah, it's the same thing. Sorry, I may not get your, so,
While you are measuring the voltage across the dummy load, and also you're measuring the voltage across the shunt resistor.
yeah, because I measure the voltage across the dummy load and the shunt resistor, I to calculate the total voltage and multiply by the current, because I measure the voltage across the
Where do you
shunt.
get the current?
The current I get from calculation from the voltage across the shunt. Yeah.
So you
Yeah,
measure,
and then,
you measure.
no, I cannot measure the current in the circuit, so I just measure the voltage across the shunt and then multiply the current with the total voltage. Yeah, I get the power.
Okay. Can you go to your results for not this one, but any other one? Just show me two, like 10 and 20 degrees. Okay. You see here, maximum power, maximum calculated power. What? Did you calculate that?
Yeah, I calculate that based on this is actual power
Okay.
from the data.
So
Yeah,
maybe you should be clear there, okay? The other thing is, right here is, your 45 degrees is a constant or is it changing system? Is it a reference system?
Yeah,
Is it
45 is
reference?
reference system at the optimum trigger, and I choose 45 as optimum trigger.
Okay, and you say you normalize, I mean, you're getting 19 watts there, you normalize that to 100, right?
Yeah.
Okay. So keep that in mind, go to the next slide or. Okay. Now, with the same system, you said like 45 degrees is still your reference. But right now, no, go to another one, not this one. Just to move forward. Okay, 45 degrees. So right now, my maximum is 20 for the same system. What changed? Why is the 20 now is my maximum? Because it used to be 19.
The 19 watt in the 20 degree triangle is based on the calculation.
No, I'm not talking about, still, remember, we agreed that the 45 degrees is the reference.
Yeah.
So, maximum for a reference shouldn't change, right? What did you
Yeah.
change here?
Yeah,
Why
I
is-
understand. Yeah.
Why is it, if you go to another slide, like 50 degree conversion with the 50 degrees, we have another maximum there. Yeah. So every time you change the tilt angle, actually your reference system actually changes. Right?
Yes. Yeah.
Is that right?
Because this is the actual power, so based on my calculation on the actual data, I get the actual maximum power. Yeah, so that's why it's different. So that's why I set the data to the power rating to 100.
You gather data for so many days with the same system, the 45 degrees, and every time you change the maximum of that 45 degrees. That's my understanding of your table there. My question is why?
Yeah, because the actual data, the actual power is cannot the same. Because when I do the comparison, I example at 10 degree triangle,
Yes.
I measure the data, I collect the data in certain days, and then I move to 20 degree triangle. So they are at different times. So that's why the calculate power, the data is different. So the calculate power should be different.
I understand that the power would be different, but the maximum should not be different. I'm not sure if you understand.
Yeah, this is based on the average maximum calculated power.
But if you have a
At
car with
different-
a
at
maximum
different
speed of
one
200,
time.
if you have a car with maximum speed of 200, and you drive in that car in a sunny day
Yeah.
to the maximum speed, does the maximum speed changes if it's a rainy day?
Yeah, in the rainy day it should be changed compared to the
Does,
sunny day. Yeah, because you cannot ride maximum as the when in the sunny days.
okay. I
And
guess your reference shouldn't change. That's my comment there. Your reference shouldn't
but
change.
actually, yeah, I understand. But actually, you see the data because the data, the calculation based on the data at different point time. So the powers, I cannot get the same. This is actual. That's why I shift to 100 watts. Yeah.
Okay. The other question is, or maybe a comment there. The table there explains the cost per, like how much I would pay per watt if I want to go with any option there. So for me, I need to do the calculation to figure out the final number there, and it didn't show like the final number. Because you made the conclusion that say, okay, adding more panels would be more beneficial to the customer or to the client or whatever.
You see the cost for install watt extra if you go with the adjustable option.
I understand that.
Yeah.
My comment is, I still like as a viewer there, I still need to do calculation in my head to figure out how much it's actually going to cost me to add one more panel.
Oh, yeah.
You get it?
Yeah, because in the PowerPoint I do not put the detail on calculation.
Yeah.
Yeah.
Thank you.
Yes, thank you.
The next presentation is ready.
I like the idea.
The other thing, no one you won't see if you find it reading one all.
If I see a flag,
Gen Z.
So the person did, would probably be, like if you had a person that did it 4/7, probably.
Well, that's it looks like a very cool as a person, right? Observing the style. Oh, it's not a reality. You would tell it to bring it in, but it doesn't really have that.
Sorry for that. I was trying to read as my body.
What did I do? I'm innocent.
Have very unintentional ways of saying
It all works except for the gain function. Well, when I did, I like to use
because I was 06. He was we're not going to be available.
I don't think you realize how.
Yeah, it's going to be a new PCB.
How I would know right away.
There's a tweet on the stand. Oh, sorry, we have
You said so.
I'm gonna go see it. I got a few minutes.
It's kind of.
I'll try. I'll try.
I could add, just start adding.
I'm not sure.
Oh, whoever's sitting in this seat, that's the introduction seat, so you have to do the introduction.
I'll do it.
No, as long as you let me in.
Can't promise. We expect a little song and dance, a little cha-cha-cha. I could do some pushes.
You think I do perfection? I evaluate the talk to a table over at the same time. I didn't realize there was that much.
Yeah, there's there is.
These ones are diverted here.
Which is surprising. I don't think
economy here.
yeah.
Because it has to be weighted enough to stay.
So it's also for it to on stage.
That's right.
They moved the CD. That's it. So that's actually very scale. The CD will stay that way.
It's more of a pivot.
And that's all they're doing. They're moving the CD around. That's really cool.
Yes.
Neat, eh?
The actual thing is this. So that's where it's if it's lower than this,
It'll fall down.
yeah, when you go here, now it's higher than this.
Yeah.
That's really
All because I almost spilled Erica's drink. Very subtle.
What are you doing this time?
Yeah.
I remember that from friends.
Yes,
Friends. Yeah. You've truly been Western.
This is how it went
Right.
Yeah.
By watching friends.
Different, we've been watching a lot of stuff. Yeah.
Yeah, better introduce. You want to lock that door?
I think it is there.
Is it locked?
No, I wouldn't. Oh, somebody else. I didn't move. I was running back.
Doc Martin's name is better running shorts.
Okay, welcome to the second presentation of the day. Just before we get going here, I would like to acknowledge our online guests. So we thank everyone who's been attending online this week and watching the presentations. And I'd also like to just give a special word of welcome to Anthony Black and MJ Gadet from NAV Canada. So they're here with us today. Anthony is a graduate of our program, what year, 2008?
2011.
Oh, 2011, okay, yeah, 2011, and I think it was Anthony that had the reputation as being the best prankster while he was here, wasn't it you?
No, I don't think so.
I think it was. So anyway, without further ado though, we're going to have Mr. Gagandeep Singh present on his water tank level controller.
Good morning everyone, my name is Gagandeep Singh and my project name is Water Tank Level Controller. It's an electronics type of project. So starting with project aim. So what was the aim of my project? So my aim was to develop a water tank level controller system so that I can control the filling and like draining process of water in tanks. Next, I wanted to have a user-friendly interface, like something I can control, something with buttons, and something that will have visual indicators that I can know how much water is left in the tank. So that was my aim. And next was to promote water conservation so that like the tank doesn't spill water, and so I can save water with that. And the filling process stops automatically, so there is no wastage of water. And next, so why did I go with this project? So I have a kind of personal experience with water management. So back home, like we have water tanks in our houses. I belong from a state which is like very diverse in agriculture. So we don't get water like 24/7 on a day. So like there's a time of a day where we don't get water. So like each and every house has their own tanks. We never use direct supply of water. So this is very common in India. So every day we used to fill up our tanks, and the problem with that is when we fill up our tanks, we didn't have any knowledge that how like when the tank will get full, and the only way we know the tank is full like when the water starts spilling from it. So that's water like getting waste. And moreover, it's also beneficial for people. That same reason, there's no like availability of water every time. And next is I also wanted to automate the thing so like it can stop, fill automatically. So the idea that came was to build a device that helps the user to control the fill and drain process, as well as to keep track of amount of water that's left or that is being in the tank. So that is my concept drawing. There's an ultrasonic sensor on the top. That's what I'm using to measure the water level. There's two DC water pumps. One is for filling it and one is for draining it. My enclosure. And there's a toggle switch that's used to turn it on and off. It's a single pole, single throw switch. And there's knuckles for wall adapter, wiring, 3 push button switches. One is for fill, one is for drain and stop. And I have LED indicators as visual indicators. Those are 10 multicolor LEDs in a row that will tell me how much water is left in a tank. Moving on to the block diagram. So for the power, I'm using a wall adapter to power up my circuit. It's a wall adapter that will provide me 4.5 amps of current, and it will give me 12 volt. And that 12 volt is used to power up my pumps. Both of my pumps are 12 volts and they require 4 amps each. And that 12 volts also goes into my voltage regulator. It's a buck regulator that helps me step down it to 5 volts. And for the water level sensor, it's an ultrasonic sensor that also needs 5 volts. And for the microcontroller, I'm using at Mega 328P. I have 3 push buttons, fill, drain, stop, 2 MOSFETs to drive the pumps, and water level indicators as 10 LEDs. The fill, drain, stop are momentary push button switches, so they will come back as soon as you press them. And water level indicators are 10 LEDs in a row. Dotted lines represent a user interface, and water level sensor is ultrasonic sensor. So this is my flow chart of the program. This is start. I'll then initialize the pins. So in the start, it will read the water level using the ultrasonic sensor. As it will read the water level, it will update the level indicators as soon as. So there are 3 buttons, fill, drain, and stop. So suppose I press the fill button. So it will go to a condition like, is the water tank already full? Suppose it's not full, so it will signal the MOSFET to turn on, and that will turn on the fill pump. So the water will start filling in. And it will keep checking. Is it full? Is it full? Is it full? Suppose it's get full. So it will stop the fill pump, go back again, update the LEDs that much water is in the tank. And suppose I press a drain, it goes in the same process. It will check if the tank is empty or not. No. It will go to the MOSFET, turn it on, turn on the drain pump. Drain. Oh, it's empty. Yes. So it will stop the drain pump, go back, update the LEDs. Suppose I press stop in between the fill or drain process. So it will halt any ongoing operation. So like if I'm filling, it will stop, or draining, it will stop. So this is my schematic. These are my inputs. This is my voltage regulator. This is LM2596. I have 3 push buttons at Mega, and I have 10 LEDs that are Charlie flexed and ultrasonic sensor, and those are my ICSP connections for programming in case I need it. And I'm using 2 MOSFETs to drive the pumps. So in the schematic, I'll move forward to the voltage regulator. So it's converting 120 volt AC to 12 volt DC at 4.5 amps. So the regulator is a buck regulator, it's a switching regulator, and it has less power dissipation, so it doesn't like, in compared to linear regulators, it dissipates less power as heat because it uses switching mechanism to step down the voltage, so it's better than linear regulator. So, and the 12 volts, as I said before, it's used for my water pumps, and the 5 volts for Mega 328P and for ultrasonic sensor. Moving on to the microcontroller. So why did I choose to have a Mega 328P? I was very familiar with this chip. I worked a lot of labs with it, so I knew most of the chip, like how to use it. And the second thing is, it had wide range of input and output pins. Like I don't need to worry about any pins, like if I get shut off. And moreover, integration with other components. I could use it with most of the sensors and things. And it was programmable in C and C++, which I learned during this course. So this was helpful for me and convenient. So moving on to the outputs. So I am using N-channel MOSFET. It has a fast switching speed and low resistance. I think it has 22 milliohms of internal resistance, so it dissipates less power, and it's very convenient. And for the pumps, I'm using a flyback diode because they are inductive loads. So in order to protect my circuit, I'm using a flyback diode, and the pumps are 12 volts, 4 amps each. So for the LEDs, I thought to try a new thing. So I use just 4 mega pins to drive 10 LEDs. The method is called Charlie plexing. It is to drive large number of LEDs from a few number of pins. So it is like a matrix of LEDs. By switching on the pins high and low and turning some pins input, you can control a large number of LEDs from a few pins. So the thing to do this is you need to be fast because it is switching. I need to turn on 10 LEDs, I need to turn on first, then turn on second, third, fourth, fifth. I need to do that fast so that all 10 of them seem to be turned on at the exact time. I'm switching on 1 LED per time, but I need to show how like the 10 LEDs are on at the same time. So we need to be fast so that our eyes see that both the 10 LEDs are on. So that's the only thing. If you add any kind of delay in that process, you will just see only a particular LED to be lit and others to be dim or turned off. So that's the thing. You need to be fast with doing Charlie plexing. For the inputs, there are 3 push buttons: fill, drain and stop. And I have used internal pull-up resistors so that I don't get any miss. And for the inputs, I also use an ultrasonic sensor. So for the ultrasonic sensor, it has 4 pins. The main 2 pins are trigger and echo. In the code, I am just sending a 10 microsecond pulse, and it will wait until the pulse gets reflected back to the echo pin, and it will start a timer. When the trigger pin sends a pulse, it will start a timer, and when the pulse hits back on the echo pin, it will stop the timer, and it will count the time for how long did the pulse take to come back, and depending on the time, it will calculate the distance, how far the object is. And moreover, ultrasonic sensors, like CSR04, it has a good accuracy. And this is my PCB design. This is my back copper. I tried to put most of my tracks on the back copper, and there are some tracks that I need to be like of more width because of the high current that was flowing through my circuit. I was driving 4 amps from my circuit, so the track you can see. I'll just show you. So this track, so this is a wider track as compared to others because it had to support 4 amps, and I did the calculations, and based on the calculations it was around 70 mils, so that could support easily 4 amps, and I need to make my pads also wider so they don't burn out. And for the front copper, I had only few tracks, and I also used vias to connect them to the back copper because we have problems soldering the pads on the front copper side, and moreover when there are components on the PCB, it's very tough to assess the pads. So this is how my final PCB looked like. There's some issues in it, like the resistors. Those were design issues. Actually, I wanted to have pull-up resistors, but I put pull-down resistor and connected them to ground, so they were not working. So I removed them and I used internal pull-up resistors for the buttons. This is my enclosure, and all the measurements are in inches. I ordered my enclosure from Hamad Electronics. So what knowledge did I gain in this project? So it helped me a lot in improving my programming skills. I learned a few new techniques. It obviously helped me learn PCB designing. I designed my first PCB. Moreover, it helped me in project management, how like the project works. So if I want to work in a company, I want to go forward with the project, how the procedure works. I start with the proposal, I have to maintain a logbook, I need to follow deadlines. So it taught me that. And next is component research and budgeting. So like making the project, which component suits me, how much current rating should it have. So it taught me that how much, what type of component should I use and the next budget. So like I should not also go up beyond my budget. I need to find components that fit my description and also that fits my price. So there were a lot of things that I have to add or improve. The first is interfacing the ultrasonic sensor with Omega 328P. This was not an issue actually, it was working, but when I designed my PCB and put the things together, I was facing issues because my ultrasonic sensor was not working. The reason I think is the high current that was flowing through my circuit. I have like 0.8 amps of current flowing through my circuit, and my sensor was also getting too hot. So when I did some checking on my circuit, I think it was the voltage regulator. I think it shorted out and it was delivering more current that it was used to. But I'm lucky my Omega was still working on like 0.8 amps of current. Next is to add a switch, to switch between manual and automatic mode. Right now it's just manually. I press the fill button, it will fill. I press the drain, it will drain. In automatic mode, it will just, when the tank gets empty, it will automatically start filling up, and when it's get full, it will stop it. So it will have a certain level, a threshold. When the water falls under it, it will automatically start filling up. So I don't need to press fill anymore. And most of the components should be like the external components. I need to make them water resistant. Suppose I'm putting it in close to a water tank, just next to a water tank. Suppose and there's a water spillage or anything, any incident. I need my things and my enclosure to be waterproof and water resistant. And the next one is add fusing to my circuit. That's a major thing. I didn't get it. My circuit has 4 amps of current flowing through it, and I didn't add a fuse. So fusing is very necessary. And component placement in my PCB design. So like there were terminal blocks in my PCB. Those were arranged. If I go back and show to you. So as you can see my terminal blocks, 2 of them are on the bottom side and 2 of them are on the right and 1 is on the top. So I had difficulty opening my enclosure because when all of the wires were attached, I couldn't open up my enclosure fully and assess the PCB. So the next time if I have to redesign it, I'll put all of my terminal blocks on one side so I can easily assess my PCB. And next is to improve the handling capacity of my PCB, the current handling capacity of my PCB. So I can use better pumps. So suppose that this pump supports only 4.5 liter per minute. So it has capacity. So if I use better pumps, I need more current. And next is being cost efficient. I had some parts that were expensive, which I could have bought cheaper. So the last point would be cost efficient. So conclusion. So it was a great learning experience for me. I learned a lot of things, especially project management, and I think all of the skills would be beneficial for me in the future. And it helped me create a device that is helpful in water management and storage. So these are my references. This is for the enclosure that I showed you. Thank you. So I'll demonstrate my project. Before demonstrating, I want to say that as I said earlier, I had issues interfacing my ultrasonic sensor because of the high current, and so it's not fully functional. I just used some changes in the programming, and I'm just faking the data from the ultrasonic sensor in the programming. So it will show that the water level is increasing as I press the fill, and the water level is decreasing as I press the drain. Okay. So I turn on from the switch. So it's showing me that 50% of the tank is full by showing the 5 lit LEDs. So that is the supposed water level in the beginning. And if I press the drain button, so the pump is activated, it starts filling the water in the tank. And as you can see, the LEDs also start lit up. It will show that the water is increasing in the tank, and it will go on until it's full. So you can see the LEDs blinking. This is because of the Charlie placing. They are switching on and off at very high speed. So you can just see flickering in the camera, but in real time you can't see it. And if I press the drain, it will start showing me that the water is draining from the tank. And at any point, if I want to press the stop button, it will stop everything, and it will show that the water is at the same level. It will stay at the same level. And if I press the fill button again, it will start filling up again. I should stop as soon as it's filled. So that was for my demonstration.
You might as well take us to the first slide on your schematic. I think unless somebody wants to listen. Like, I mean, the first, yeah. Okay, maybe we could start here. What type of diode is D1?
I think it's a Zener diode.
Is it a Zener?
I'm not sure about that. I will not say like 100% is a Zener.
You're not going to say 100%?
Yeah, because it's different.
What's the symbol for a Zener? Is that the symbol for a Zener?
Yeah, I don't remember it. That's why I can't say.
It's not the symbol for a Zener, is it? So it's not a Zener. So what is it? You don't know what type of diode that is?
I don't remember the symbol.
Is that the type of diode that you have installed on your PCB?
Yeah.
Yeah. So it's not a standard diode, is it?
Yeah, it's not a standard.
When you buy it, what was the description of the diode?
What's on your parts list in the description column for that diode?
If I would have remembered, I would have told you.
Yeah. Yeah.
Might be a good idea to have things like that on hand.
You probably should know something about that diode.
Well, here, I'll go a step further. That LM2596 is a programmable buck converter. How does it work? How do you program it? The output can be a variety of values.
No, it depends because there are two kinds. It's a fixed output one, and the other one you're talking, it's adjustable ones.
According to the spec
So,
sheet I
like,
was looking at.
LM2965/5, 5 represents 5 volts of fixed output.
So how does it work?
So it will take the 12 volts from V in, and So, and it has a MOSFET in it, if I say. It's a switch on and off at high speed and
What frequency?
150 kilohertz. So, and the diode and the inductor, they form a LC circuit.
LC circuit with a diode?
Yeah.
A diode?
Because it's switching fast, so it's not
What do you
that
need for an LC circuit?
it's providing constant power to the.
No, what do you need for an LC circuit?
What do I need?
What components do you need for an LC circuit? You have an L, you have a C.
Yeah.
Where?
C is the capacitor, C2.
Okay, you think that's the LC circuit? Not the diode?
I think those three are there for stabilizing the output
Stabilizing? What do you mean by stabilizing?
because as it's switching, the inductor, it will oppose the change and it will make a loop kind of thing. So
Kind of thing?
when it's off, it will provide the power. When it's on, it's going directly to it.
Well, when it's off, where does the energy come from?
It comes from the capacitor.
Okay, and when it's on,
It comes from the regulator itself.
from the what?
The regulator itself and the inductor
The inductor. So what's D1 for?
to form a closed loop with the capacitor and the inductor, so it can supply power
When?
when it's off.
When what's off?
The regulator when it's switching the MOSFET.
There you go. What's pin 4 all about?
Pin 4. So it's a feedback to tell the regulator like it's not 5 volts to make the switching speed kind of that so that it can regulate the output to 5 volts.
Okay,
If
so
it's,
does it increase or slow the switching
it
speed?
depends.
If it's
It depends if it's more than or less than.
okay, so if it's more, then what does it do?
If it's more than 5 volts, it will slow down speed, switching speed, and if it's more, it will.
Okay, why? How does that fix things?
So it's like a PWM cycle. So it will increase and decrease the duty cycle. Kind of thing.
But that's not switch speed then. Those are two different things, duty cycle and switch speed. You're explaining two different phenomena there. Okay, well, maybe we'll go on to something else.
Yeah, let's go on to, maybe just go to the next slide and see what's next.
Yes.
Or maybe the next one after that. Yeah, how about this one? This is a good one. So you mentioned that each pump draws 4 amps?
Yeah.
Yeah. You referred to D2 and D3 as flyback diodes. What does that mean?
It means whenever I turn off a pump, so there might be voltage spikes that might be. That might be greater than the reverse voltage of the MOSFET, so it might damage the MOSFET. So by adding a flyback diode, it will.
What causes those voltage
It's
spikes?
an inductive load, so
Huh?
inductive load, the water pumps.
Okay, what
So-
causes what? So
It
the
will
pump
oppose-
looks like it's like an inductor, right?
Yeah, so it will oppose the change and it will continue.
Oppose the change of what?
Oppose the change of the, like, when it's switched off, so there will be no
Oppose the change of what?
Oppose the change of the current,
The current.
Yeah.
The current where?
current flowing through it,
Through what?
the inductor.
Through the. I can't hear you. You need to.
Through the inductor,
Okay, so the pump, which looks like an inductor.
Yeah.
Okay.
so when we switch it
So-
off, so it
So
will.
what happens as a result?
As a result of what?
of the current that wants to continue to flow?
So as a result, so it will act as a source.
Yep,
It will act as a source, so the current, it will discharge, the inductor will discharge, and
it's not discharging per se, because inductors don't store charge, do they? Yeah.
so the diode will help to protect the MOSFET. That's it.
So what happens as a result of this current that continues to flow, even after, what has happened, you've shut the pump
So
off,
it will,
right?
yeah.
So the inductance of the pump causes, like you said, the current to continue to flow. Where does that current want to flow?
It wants to flow to the
If the diode wasn't there?
lowest resistance point.
Yeah, okay, if the diode wasn't there, right?
Yeah.
Where would it want to flow?
Go to the ground, to the MOSFET. That's
Through the MOSFET, right?
Yeah, yeah.
Okay, and so what's the impedance of the MOSFET
It's
in that?
22 milliamps.
What's the impedance?
22 milliamps. The
Huh?
resistance. 22 milliamps. I
When
think.
it's off, in off state?
In off state, I don't remember the exact value.
Well, would it be,
Theoretically.
yeah,
It will be much higher.
it would be very high, right?
Yeah.
So, I don't know, just put a high value on, like an open switch, what would be a high value of resistance?
High value.
Yeah,
Can't be any. Gigs of volts.
how many ohms?
Data gigs.
Okay, let's say, I don't know, let's say, just to make the math easy, let's say it's a mega ohm even, right? So how much voltage would be across your MOSFET if it's 4 amps?
How many ohms you said? 10?
If it was a mega ohm,
Per mega?
right? And you have 4 amps that want to flow because of this inductance, right? What's the voltage across your Q1 there?
4 mega?
4 megavolts, right? So what's the diode do
It will just
to protect?
burn out.
No, what does the diode, now you put the diode in, right?
It will start conducting, so it has a
Okay.
peak reverse voltage. So if you cross that area, it will start conducting in the opposite direction.
So the diode does what?
So it will protect. It will just send back the same current to the pump itself.
Okay,
Yeah.
so it's
So it
going to
will-
cause,
Yeah.
So how much voltage will be across the,
so, yeah,
the gate, the drain source?
yeah, how much voltage then would be across Q1 with the diode installed?
Across the diode.
Across the Q1, with the diode installed, how
With
much
the
voltage
diode
would be across
installed.
Q1 instead of 4 megavolts?
It will be pretty less. It will be approximately 0.
Not 0.
How much is going to be across the diode when it's conducting?
When it's conducting, it will be depends.
What type of diode is that? You didn't know the other type, but maybe you know this type.
Is it normal?
A normal diode, yeah. Can you define what normal is?
All these diodes.
What type of semiconductor material? Yeah.
I have no idea about the material.
Huh?
I have no idea about the material.
You don't? Well, there's only so many semiconductor materials. I mean, we have germanium. I mean, we can start listing them. Starts with S. Silicon, right? So what's the drop across the silicon diode when it's conducting?
What's the drum?
A typical value that we use quite a bit.
0.7.
0.7, right? So 0.7 across the diode. So if 0.7 across the diode, what's the voltage across Q1?
0.7.
0.7?
4 megavolts minus.
You have to use KVL here. Okay? Can you use KVL and tell us what the voltage across Q1 would be?
Next question. All right, well, I'll let you figure that one out. R9 and R10, what's the purpose of those? Why do you have to put those in?
So the gate, it doesn't, it's connected to the ground, so the float,
It
and
doesn't
disconnect
what?
floats,
Loads?
because it's a voltage. VGS is, this MOSFET is N-channel MOSFET is voltage regulated, so it needs voltage to turn it on and off. So I need to put it to the ground so it doesn't disconnect. Like pull up, pull down, pull down.
When you put a voltage across out of pin 5, would that not be a voltage to ground? Why would I need a?
Because
You're right, it's a voltage control device,
but there's
but it's also what's the impedance look like when you look at the pin 1 there? The gate,
impedance.
5 ohms, 50 ohms, 50 mega ohms.
It would be the next. Because it's kind of parallel to the pin 1, the R9,
What's parallel?
the resistor. So voltage will be the same across both of them.
Again, if you remove R9 and you place 5 volts to ground out of pin 5 of the MCU, there'll be 5 volts there too. Will there not?
Yeah.
So why do I need R9?
So in case there is no 5 volts, so.
Well, then it's 0 volts, it's gonna go to ground.
But it will be a short, kind of a short if there is no resistor.
It's gonna be a what? If I place PD3, pin 5 is 0, whether there's R9 there or not, it's gonna be 0, it's gonna be ground. If there's R9 there, it's gonna be ground there too, no matter what. Dan, what does pin 1 look like? What model could you use? Basic capacitor, inductor, resistor, when you're looking at the pin 1 of the Q1 there. What does it look like? Does it look like more like a resistor? Or it looks like more of a inductor or a capacitor? Looks like a capacitor, exactly. It's layered, high impedance, very high impedance. So that means when you place a voltage on pin 5 there, what happens to that capacitor? It charges. If you remove the voltage, what happens to that charge? It kind of stays there, right? It has the possibility of either staying there or not discharging very quickly. But with R9 there, what happens? It'll discharge. Okay.
You made specific reference to these N-channel MOSFETs and their fast switching speed. Why is that important in this application?
It is not important, but suppose I want to play with the buttons, I will not have any delay.
Why is the delay important?
I said it's not important, but still.
So why did you mention it as such an important
It's a
feature?
factor of the MOSFET, MOSFET.
Yeah, but why, like, that's great and everything, but why is that important to your project?
It's not important, I said.
It's not important, so you're just using it to fill time then, is that?
It's like specialty of a MOSFET I'm using.
But why, like, I was just wondering why it was worth mentioning here.
As I said, like, if I want to play with the buttons.
That's the reason that you needed a fast switching speed in case you wanted to play with the
I
buttons?
don't need it, but it is there, so why not mention it?
So how much did those MOSFET cost?
Those MOSFETs, I think $4.
You made your device cost $8 more than it should have. You're gonna make 1 million of these, that's $8 million.
Like they can handle high currents too.
Well, I was just wondering why the fast switching speed, why are you emphasizing that if it's not important to your application? It's either important or it's not. I want to know why you think it's worth mentioning.
Why did you pick this particular device?
MOSFET?
No, well, you wanted a MOSFET. So what did you do to pick this? Why not pick the IRF 542 or 563 or whatever? Why'd you stick to that one there? Did you just type in Google MOSFET? That's the first one that came out?
Kind of. I just wanted to have this.
I hope that not everything in the world is designed that way.
Yeah, by Google.
I would just pick the first one that comes up.
I had a question on the PCB. Can you go to the PCB design? I guess the other one.
This one?
Yeah, I'm gonna quote you here. You said you wanted to use pull-up resistors, but you used pull-down instead.
Yeah.
What did you mean by that?
It means that those resistors, as you can see, they were connected to the ground. And so they are pulling the pins down to the 0 volts. And I need to pull up so that the buttons stay at 5 volts.
Is that the resistors that are missing there?
Yeah.
The R1 or 2 or 3?
Yeah.
Okay, so they should have been pull-up.
Yeah.
And how did you solve the problem?
As I mentioned inside, I used to pull up resistors internally in that mega.
Okay. Could you bring up your flow chart? Okay, could you walk me through the first part of your flow chart? How did things happen in your code?
So in the initialization of pins,
Yep.
it will initialize the buttons, it will initialize the timer, the prescaler of the timer,
Yeah,
which
sure.
is 1.
Okay, so that's all done, yeah? Then what?
And so this is like multiple things happening at the same time.
Oh, no, I don't think so. Your MCU is a linear series program device. Things don't happen at the same time.
It's not voltage, right?
No, it's not.
So suppose I press a fill button. So it will go to a condition.
Yeah, but how do I go that way? Where is there a decision that says I need to go that way?
You're showing 3 parallel paths here, things that have to happen. How's that happen?
In your program, you do all your initialization and then does your program split up in 3?
It splits up into conditions,
Really?
On conditions, so where are your conditions?
button conditions. Like if I press a button.
But don't you check all the buttons at once, both at the same time?
Yeah, what's missing here?
Don't you check one after the other? So why does your flow chart not represent that?
The blocks for the buttons, are they appropriate?
No, they are not appropriate. It should be a condition.
It should be a condition.
They're driving the box.
If it's pressed, yes, do this. If not, move on to the next.
Your flow chart has to show the logic of your program. Did you do the flow chart before or after you wrote the program?
After.
Wow, that's kind of reverse to what I taught you, didn't I? Yeah, kind of solve the problem first, then write the program. No wonder your flow chart doesn't really solve your problem, right? How long did it take you to write the program?
How long? 2-3 days.
2-3 days? And if you'd written the flow chart properly, it might have only been 2-3 hours.
Yeah.
That would cost a lot less to the company, eh? You said somewhere that you used the 329 because you were familiar with it, and you also said you used it because you could program it with C and C++.
C.
C. So what's the difference between C and C++ fundamentally?
I didn't mention I.
No, you said C and C++.
I said it's programmable in C and C++.
Yeah, it's rarely programmed in C++. Why?
C is better than C++.
Why?
It's easier.
Oh, I would beg to differ on that. I can show you some stuff in C that it just hits me.
Well, I used the C to go.
Okay, so you just C, well, be careful, right? You said C and C++.
I said it's programmable in C and C++.
We'll review the tape on that one.
Yeah.
It's in the
It's
slide.
recorded.
It's in the slide.
We're in.
Yeah, right.
Yeah. Okay,
Okay,
thank you.
Undecided, we get this one, we get mine at one point, because this is gonna be one video and they're gonna use for everything. One good. I would have a challenge with because the issue is that if I have steering, throttle, and transmission, you're gonna take then if I decide to add start. Well, I don't know how that's supposed to do it. That wouldn't be able no, not more range. It was too bad, so
You're supposed to present with the computer provided, okay? So whatever is in your, what are you doing? You're simulating? You mean for the demonstration? Just put the camera on. Okay. All right. Because we don't want things like being unplugged and plugged here, and you could affect the screen. I had that issue earlier where I couldn't get it. You know,
one transmitter for the whole car.
Well, when's yours this afternoon? When's yours this afternoon? What's next week? Yeah. The room is, I sent an email out last weekend about the room. Well, I sent another email to security yesterday saying to them, just please allow anybody on the list into the room during college operating hours. Anytime this week, so up to 1 p.m. on weekdays, over the weekend, during operating hours, okay? So what's that? I think it's 10 to 5 on 10 to 5 on Saturday, and 12 to 9 on Sunday. 12 p.m. 12 p.m. So anytime you're in an hour of like 4 a.m. on the front entrance, the main entrance. Yeah, anytime during operating hours, practice. And I'll be preloading the presentations that were submitted via Brightspace each day. Okay, so. No, that computer is not connected to Wi-Fi. What do you need? Why do you need Wi-Fi? We can join it for your presentation. You're going to access the Wi-Fi. Yeah, it's not connected to the internet. The reason is I want to pre-link it to the presentation to updates or something. Yeah, that's fine. If you want to use the Wi-Fi to connect to your device, yeah, you can do that. Do you have your device here right now? Okay, you should check that well in advance. Because if there might be an issue and we might have to get systems in here to give us permissions to do something. So, because that computer is locked down, like, you know what I mean? Like, you can only do so many things on it. In fact, I created a folder to put the presentations in on the hard drive. And I named the folder Day 1, thinking I'll delete that one and put another one in. That won't delete it. It won't let me rename it. But not deleted and not renamed. So I only have the ability to create the file but not modify it. So I have Yeah, you can do that. I would have that ready to go in the see when we go here Monday, Tuesday last, Tuesday 9:30. So what I would do is in a 15-minute break, as soon as Daniela is done, I'd be going up there and making sure everything's loaded and ready to go. Oh yeah, test it. If you can do it tonight, that would be much better, because let's say that you can't do what we need to do because of a permission issue. We need to go and talk to somebody in IT, get them to come down and say, if you come back tonight or after 3, Okay. You got your presentation in there? For notes, yeah, yeah. I guess that's what I said. Somebody can. You're gonna do it? Okay. Who's your man? Yeah, the time is terrible. Okay. All right, I sit on the end. It doesn't matter. Okay, the next presenter of the morning is Gretten Zarzuela, and he's going to be talking to us about his automated vertical parking system. Go ahead, Gretten.
Thanks, sir. Good morning, everyone. Thank you for being here today. My name is Greta, and I am delighted to present to you my project, Automated Vertical Parking System. So in the next 20 minutes, I will discuss and provide an overview regarding key points on the introduction, concept drawing, block diagram, wiring diagram, testing and results, conclusions, and future improvements. So for introduction, what is the parking system, automated vertical parking system? Automated vertical parking system is a type of parking system, automated parking system, that park or retrieve a vehicle in an efficient way in a vertical design. So what is the difference between automated and traditional? In a traditional parking system, parking space are utilized in an inefficient way, and most of the large areas are used by ramp and lanes, which can result to lower capacity. And the traditional parking system also time consuming when searching for available parking slot. And it also lacks security. Unlike the automated parking system, you can add security and increases capacity up to 50%. So for my concept drawing, I use 11 sensors, proximity sensors, and 3 push buttons. For my inputs, digital inputs, and for pin number, I use one analog input. And for my output, I use the 2 DC motor. This one is used to lift the scissor lift, and the other one is to extend, or I call it the scissor lift extender. It should be the same. And this pin knob or pin number will use to input the pin number that should match to the designated each parking spaces. So this is the top view of my concept drawing, and I will display the pin number using a voltmeter module that read the voltage across the potentiometer, and using a park push button or retrieve push button, it will be park or retrieve, depends on the parking status of the parking spaces. So this start or stop is designed to start the operation and stop and put the lift on the standby level, so it will for maintenance or for emergency, something like that. So for my block diagram, all my inputs are going to the PLC, programmable logic controller, and for output I use a 24 volt DC motor for scissor lift and a scissor lift extender as well. So for the sequence of operation, I will use this block diagram to explain each of the input and outputs. So for my sequence of operation, at first, at initial position, the scissor lift is in standby mode, and it will be in the level of standby level proximity sensor. So if you push the push button operation mode, the scissor lift will move upward until it reaches the ground level proximity sensor 2. And then at this status, the user can now use the system and if the user input its his or her pin number using the pin knob, the potentiometer, it will be displayed on the pin display using the voltmeter. And after that, if the user push the park or retrieve button, it will be parked. Depends on the parking status, which I stored on the data block that I use on the program. And after that, the PLC process the pin number, which should match the pin input and the stored pin number on the each or one of the designated parking spaces. If the pin number is matched, for example, the pin number is assigned to the second floor, the PLC will direct the scissor lift motor to move upward until it reaches the second floor level proximity, if the parking status is equal to 0, the operation will be in park mode. And if the parking status is equal to 1, the operation will be in retrieve mode. So for example, the parking status will be is 0. The PLC will direct the scissor lift extender to first extend, and then after that, the PLC will direct the scissor lift to move upward until it reaches the ground level position proximity sensor 1 to get the car. Until when the scissor lift extender get the car, it will be moved. It will be moved in retract position until it reaches the scissor lift platform, and then it will move the scissor lift upward until it reaches the second floor position proximity sensor 1 to park the car, and then it will direct again the scissor lift extender to move forward, and then after that the scissor lift, the proximity programmable logic controller direct again the scissor lift to move downward to now park the car in the designated parking space that assigned in the pin number. And now after that, the programmable logic controller will direct again the scissor lift extender to retract and then move to the initial position, which is in the ground level proximity sensor 2. And after that, the parking status will update, and it will now equal to 1. So for the parking status or all the data that I stored in the data block, if there is an outage, it will be restored to the initial value. But if we want to store that value, I think we can use something cloud storage that not really affected by any consistent power. And for the other function, it will be the same until it will be the same for each level. It only depends on the parking status, or it will be updated whenever the user use the system. So for my output, all my inputs are using 24 volts, and for my analog, I use a resistor to drop the voltage to 10 volts. So yeah, this one is the retract proximity sensor and the extend proximity sensors. So for my wiring diagram, from the 120 volt AC, I use a power supply to convert it to 24 volts. As you can see here, line 1A and line 1B. So the line 1A is going to the PLC, which here power the PLC, and these are my wiring connection. The operation mode, PB normally open, standby PB normally close, and park or retrieve push button normally open. And all the proximity sensors are normally closed, and one is the standby level is normally open. I use the proximity sensor normally closed because of the availability of the proximity sensors. When I search for an online that not really big proximity sensors and has a lot of stocks, I chose this one because I can use 10 normally closed proximity sensor, because I don't want to mix it like 5 normally open, 5 normally closed, and these 10 proximity sensors are the last available, and this one is just like 10. The normally open is like only 10 available stocks. That's why. And then here, I use the voltage divider to calculate the 10 volts drop here in the potentiometer to use it in an analog input. So here I connected the pin display, which is the voltmeter module, rated at 12 volts. So for this input, I use the syncing setup because, no particular reason, just for the availability. So this is a syncing input and sourcing out input module for the PLC. So for the output, I use relays to control the direction of the motor connected to the output, and this is connected in a sourcing output module for the PLC, and in output syncing output for the output. So this will be the connection of the relays, the scissor lift extender, extend relay, and then scissor lift extender trap relay, normally open and connected to the 24 volts DC motor that control the direction of the motor. So for testing, unfortunately, this test was not really I performed because my project last weekend not fully functioning because the sequence of operation is still not functioning, fully functioning. So, but the scissor lift and the extender is was working, but for this testing, I just assumed the the weight of the car, and then I just put some like aluminum to test the scissor lift if it can overcome the weight. And for the other age, I just assumed the time and the weight for for the car weight, parking time, and the average parking. So for the parking system repeatability, I also didn't really perform this one because but for my previous functionality, I use an HMI simulation because I still don't have the PLC that time, but for this time I compare the results for the simulation using the simulation in HMI. I usually no errors. I don't usually get an error on my simulation, and I think it's comparable to the actual, as long as the mechanism is is working. Because for the HMI, they just need to change the inputs and outputs from memory bit to actual input and output addresses. So if the program or simulation is working, as long as the mechanical is working, of course, then there will be no problem in the code. So for my testing, and using simulation in HMI, I just put just one. And then for my actual testing, I usually get an error almost every test that I performed last weekend. But yesterday, the sequence was fully functional, but unfortunately my DC motor fails, and it was I think overloaded because of the weight of the scissor lift. And if I test the two terminals of the DC motor, it's already shorted. And before the functionality last Friday, I bought 1 week before that. I bought a bigger DC motor to change the one that I have. But before that, that motor can't lift the scissor lift. That's why I just bought it. But eventually, I made it to work, so I didn't change it. But unfortunately, yesterday when I was testing the scissor lift, it fails. So for my conclusion, honestly, the most difficult part of my project is the mechanical and some delays of my parts because, like I said before, I only did the functionality last term for simulation because I didn't get the PLC, but so I tried to learn the HMI even though I don't know how to program it at first, and I know if I can program it in a HMI simulation, I just need to change the input addresses from memory to actual input addresses. That's why I'm eager to use the HMI during that time, because it can also help me during that time. And another part of this one, conclusion. The simulation, if it really works in the simulated situation, the different will be the mechanical part, how the mechanical part behaves, because that's the part when I got the problem, because my scissor lift is moving upward but slightly it's not straight, slightly leaning on left, right? Yeah, leaning on left and slightly moving forward. But it's not really big deal. But for the proximity sensor, the detecting distance of the proximity sensor is only 4 mm. That's why it's really hard to control the mechanical part. And for that, I'm happy that my project works yesterday, even though it's not my initial design. But my initial design was to get the car using its wheel, and I designed the distance of leaf extender based on the wheelbase. But unfortunately, because of the tolerance of the distance between the platform, I changed it to lift or to get the car using like at the bottom of the car, not on the wheel. And unfortunately, that's my DC motor failed me yesterday. So for future improvements, aside from my mechanical part, we can add synchronized system in smart cars or electric cars. So when you're moving around near the parking system, it will know that you're coming, and you just need maybe push your remote from the car to park to use the automated parking system. That's for electronics as well, and wireless charging for electric cars for the future. Yeah. So if you have an electric car and you want to park it on the automated parking system, you also want it to charge while in a parking. So for the next one is adjustable lift mechanism based on wheelbase of the car. So of course the automated parking system should any car can use the automated parking system, even though the car is slightly longer or slightly shorter than the standard, because I think the standard of the wheelbase of the car is around I forgot it. I searched it the last term. And the next one is the rotating platform. So it also for electromechanical, we can add an rotating platform, so you can add more vertical parking system, parking for each different direction. So for my references here, and that's all for me. And for my simulation, here's my HMI. So at initial position, we are here on the standby level. It indicates that it's activated. The lift is in this level. So if the user want to use it, for example, 1, 2, 3, 1, 2, 3, 4. if the user wants to use it, it won't function, and because you need to put it on an operation mode. So for that, let's try to operate it in operation mode. So the lift will go up, and this standby mode will be deactivated and until it reaches the ground floor or the loading dock proximity level. And then the user now can operate the system. So we try to park the car, park the car. So if the extender forward, this will be deactivated until it reaches the extend. And then it will move upward, this will be deactivated, and then this will be activated. Until this will be activated again because the extender will retract until then. After that, it will move upward again to the designated search for the designated parking space. So the user one is assigned to the second floor or the first floor of the parking space, and it will move forward and then until it reaches the extend position, and then park the car and then move downward until it reaches the second proximity sensor, which is below on the platform, and it will reverse again until it reaches the position, and then move downward again, until it reaches the ground floor or the loading dock proximity sensor below the platform. So it will be the same operation, but if we try to, now that the parking status is updated to 1, so if we try to park or retrieve again, it should be in park retrieve mode. So yeah, it will be go up until it reaches the second floor position, proximity sensor 2. And then go. The extender moves forward and then move upward to get the car. And then after getting the car, it will retract and then move downward again until it reaches the ground floor proximity sensor 1 to put the car on the loading dock, and then forward again to move the car forward and put it on the loading dock, and then the cycle will be stop, and the parking status will be updated again, and it will be equal to 0. So if we try to park it again, it will be in park mode again. That's all for my simulation.
Okay, Steve, start. Read your introduction slide. Go to the one just before that. Yeah. Let me show. Oh, yeah, so that was the next one, sorry.
The introduction slide?
Yeah, the introduction, sorry. You talked about space saving there somewhere, maximizing parking capacity, there you go. Okay, and you used the words up to 50%.
Yeah.
Is that where you got that number, or do you have anything to
No, I just read it online because
Okay.
I just
so-
assumed that because the vertical park, traditional vertical parking spaces use ramp, and that ramp has like a hole, right? And then because it
Bring up your mechanical, your concept drawing.
yeah,
Oh, bring up your concept drawing.
yeah.
So if I look at the left there, you don't have ramps, that's what I appreciate, but you've got a whole subsystem there.
Yeah.
So that's where I started thinking, well, really 50%, where are you getting that number? Okay, so.
Yeah.
When
For
I
the-
get
yeah,
numbers
for the-
that are kind of, and I started thinking, is this a sales pitch? Is this, you know, like.
Yeah, up to 50%, sir. I just read it, but I assume it's not really the minimum, maybe the maximum if it.
Well, yeah, up to 50%,
Yeah.
but if you're gonna bandy numbers like that, you better have a reference to it, or
Oh, okay.
instead of saying I read it online, you
Yeah.
better have something specific, or you better have some numbers to show that, calculations, simulations.
Okay.
You go to your block diagram. Well, you've got a,
Let's bring this up in presenter mode so we can actually see the full screen, yeah, because it's kind of small. There we go. To the block diagram, yeah.
so for me, the block, I've got a few maybe, like, for me, the block diagram, you've got a nice block diagram there, okay? But then you start explaining you said you're gonna use it to explain the functionality of your project, and then, to me, you actually started talking about the programming, really. At that point, I was kind of lost, because I thought, is this
Yeah.
really the diagram you should be using to explain your
No,
logic?
sir. No.
Yeah, it's,
Because during weekend I tried to fix my project, and I'm ran out of time to think more about my presentation. So
Okay, but did you,
I just-
you did programming?
for this field, sir,
You did programming?
Yeah.
So when we program, what do we start with?
flowchart.
So that would
Yeah, yeah.
have been a cut and paste, and there you go. shouldn't it?
Yeah. For that, I didn't use it on my project. So
Why, wasn't suitable, or wasn't a suitable tool for that, or, right? Remember, programming is just a tool, you gotta solve the problem first before you do the programming. Which comes to another point, so you did a lot of programming?
before, sir, before
No,
the here.
for your project, you did a lot of programming?
Yeah, sorry.
Hours, how many hours? A lot? How many?
Yeah, that, sir, because at first I tried to use the PLC alone, not using the HMI, because at first I am expecting to receive my PLC before that, so I just tried to
Okay.
using the watch tables.
Okay.
If I can.
So could I see some of your PLC programming
Yeah.
code?
So here, watch tables. So during this time, while I'm waiting for my PLC, I use these watch tables to watch how the system functions, but it's really hard to follow this. But during that time, I just expecting my PLC.
So what kind of programming language or did you use, or I don't know if that's what you call it?
Yeah.
Programming language you use to
Using ladder diagram.
Ladder
At first,
So why didn't we see that in your presentation? Why didn't we see any of the ladder logic, any of this? Like examples of it? You did all this work, hours and hours of work, and you know, the core of this truly is the logic. So you chose not to show a pseudocode or a flow chart, and you chose not to show your ladder logic. You chose not to show your simulations. I think that's what those are, the watch tables, the simulations. You chose not to show any of that.
yeah. And yeah, because during weekend I don't have sleep. I'm so stressed fixing my project because I want to present it here today and until mid or 4 a.m. I try to fix it today, and but
To add to that, do you have a flow chart?
I'm not sure for
You
the
don't have a flow chart? Okay.
That's the injury program.
So it was a time constraint that prevented you from getting the program into the presentation, into the file, right? Because we had a deadline when Monday at,
yeah, Monday.
so
8,
you submitted what you had for slides and
Yeah.
it didn't have those,
yeah.
right? Yeah. Okay.
I don't know if you want to.
Well, we can go back and walk around.
Yeah.
Yeah.
I have a question.
I have a question too, well, I'm doing the same question. I just trying to find it.
For your block diagram, I see for your outputs, you only have the motors here.
Yeah. Yes, sir.
What other type of outputs could have been helpful for your project, maybe for potential safety concerns?
Well, are there other outputs actually, right? Are there other outputs?
No, sir. Just
There aren't any indicators?
No.
No indicators?
No, I just use the relay to control the direction of the.
But there's no indicators at all for feedback to the user?
No, sir.
Oh. Okay. Yeah.
The motor is running, I feel like an indication for safety anyways.
Well, what about the human HMI? Is that
Well-
on? Is that not?
Well, HMI wasn't really part of it.
Yeah, it's not really part of it, but
He was
because of
using
the
it to
delay of
show-
the PLC,
Yeah.
I just use it.
Sorry.
Yeah. Well, one question here, I think that maybe for clarification on the block diagram here is, you have the pin number and the pin display. There's no directionality showing a relationship between, or the flow, okay, of what's going on between the pin number and pin display. That must be an error. There must be, like, what's the flow between pin number and pin display? Is the pin display actually inputting into the PLC as well? Because it's hard to tell what's happening there. Can you explain how that should be on the diagram?
Yeah. At first, sir, I connected it at first, I put the input here, which is 24 volts for each.
We can't see your pointer.
Okay.
Yeah.
Here, at first, my first version of block diagram, I put 24 volts here, and the pin display is parallel to the pin number, but during weekend or before I submitted my final report, I changed it to pin knob instead of pin number. So
Okay.
and but for the meeting.
So what about the pin display? Because it's unclear as to sort of what the functional flow is here in the pin display.
Where does the pin display, where does it send a signal to? I don't understand.
Is it?
Input.
It's
Is
like
it-
a display for the voltage.
And that's-
What kind of display is it?
Continuous.
What kind of display is that?
Using a screen, sir.
What kind of screen? Like-
Voltmeter, LED.
So it's an LED, like a 7 segment, or?
Yeah, 7 segment.
So how is that inputting into the PLC then? I can't tell, there's no arrow there, so I can't tell, but it looks like it has an electrical input
Yeah.
and then an electrical output.
Yeah, I just put it just to read the voltage drop on the
No,
potentiometer.
I
But-
know, but how should it be on this diagram,
Yeah,
right?
yeah.
That's a question for you to
Yeah.
answer, okay?
Yeah. For
Yes is
me,
the answer.
Yeah, for me, I just put it to display the voltage drop on the pin number or pin potentiometer. But yeah,
Then what works-
it
So-
should not be there.
So how should this diagram be revised so that we can make sense of what's happening here? That's a question for you to answer.
Pardon, sir?
How should this diagram be revised in relation to the pin displayed block? Okay, how should it be revised so that we can understand how this is gonna work?
So it should be removed on that part. And
Which part?
The pin display, sir.
Which part of the pin display? You're talking about removing something.
Yeah, the pin display.
The
The
whole
block
thing?
pin display.
The whole thing should be removed?
Yeah.
So you're removing it totally from the project?
No, sir.
Okay.
Because the display is only displaying the voltage drop on the pin number for the potentiometer, but it doesn't do anything to the PLC.
Okay,
So the pin number is the one sending signal to PLC.
Okay.
Yeah.
So what part of the diagram should be removed? Not the whole pin display, but what part of the diagram?
What part of the diagram?
Yeah.
You had to edit it.
If you were gonna edit this diagram to fix it, what part would you remove?
The pin display, sir.
The whole block?
Yes, sir.
You take the whole block off? You would remove the pin display block from the block diagram and not have it at all?
Yeah, because the display is only displaying the.
Yeah, but doesn't it belong on the block diagram? If it's part of the project? So I want to go back to my question, what part of this diagram would you remove? It wouldn't be the pin display block that you would remove, because it's part of the project, it has to be there. But what part would you remove to more accurately show how this works?
Oh, the connection.
The connection,
Yeah.
where, which connection?
Uh,
Only two,
And
okay?
the P number.
There's two connections, right?
Yeah.
There's one on the left of pin display block, and there's one on the
And
right,
the PLC side.
on the PLC side,
Yeah.
right? So you would delete, so basically the one your pointer is touching, right?
Yeah.
You would delete that, right? What else would you do to make it clear how this pin display block works?
Put the notes, sir.
Not a no. Is the pin display feeding the pin number block? It is?
No.
No?
So
So what would you do to show which one's feeding what?
yeah, by removing the disconnection.
Yeah, you're gonna remove that connection. Okay, so you're gonna remove the line, that 90-degree bend line from the right of the pin display.
Yeah.
Okay, then you are left with the line to the left. Okay, so what else will you do to indicate flow?
Put it on the before the pin number and put an arrow to the pin number.
Okay,
From
which way will the arrow
display.
will go? Which way will the arrow go?
Here.
From where to where?
From pin display to pin number.
So your display is feeding the pin number block?
Or the other way.
The other way, right? Okay. Had to go in the other Okay, any other questions? You got one?
I have one.
Okay.
If you go to your test two, yeah, your results. So this is the simulation. This is the results of the simulation, right? Did you do the actual test?
Yes, sir. For my actual test, actually the project is working on last weekend, but the sequence of operation is not fully functional. That's why I consider it, sometimes it's working, especially when moving from park mode to moving upward to this designated parking space.
So my question is, do you know why your project isn't working?
Yes, sir.
To find
Yes.
out?
Yeah.
Why didn't you say?
The project is not working because of the tolerance of it's really hard to implement because of the tolerance of the potentiometer, proximity sensor, because it only detects from 4 millimeter distance. And my problem is when the scissor lift moving upward, it moves some distance from right to left, and then front to back. So yeah, so if the proximity sensor is here, sometimes at this point it's okay, and then while moving upward it goes backwards a little bit, and then the proximity sensor at the upper level is not detecting the sensing metal, and then after that, if the scissor lift moves downward, it moves different way. That's why when I try to move the proximity sensor a little bit to sense the distance of the sensing metal while moving upward, but from after that moving backward, it will move front. That's why the sensing metal will what do you call that? The metal will get the the proximity sensor. It's okay to move like this, moving upward, but after that it will collide on the, because moving upward and moving downward is different. That's why it's really hard to adjust.
Thank you.
Yeah, thank you.
Here, you only need this PowerPoint, and folder. So the folder, just need to open it, and then I have demonstrated it is good.
If we had enough of those things we have, be careful. We had, from Michelle.
Because
Show here is not we got the x-rays from Michelle. So your presentation is already loaded. We're gonna load it right now.
Yeah, I appreciate it.
You can't load, anything different than what you submitted because I'm holding everybody to that. Okay? So you're next, right? Okay? So whatever you submitted is what you have to use. Right? That's it. Whatever you submitted in first phase.
That was kind of my observation.
You should have reached out
It is what it is.
He had it. We can talk to him again when he comes back.
I wish I would have had more time. But it is important, right? A lot of time.
Well, you'll have to talk to him. We're not allowing anybody to solve the life anything. That's the whole point of studying when, so my competition to the advisors was that we should get to the whiteboard here because we said as it is, I'm very around. I'm allowing you to do it.
I think it's okay. We don't know if it's necessary. We all know.
Because how does that relate to everybody else that's doing it? Unless your advisor thinks that that should be allowed. You should have thought of that. It took me a half an hour of my time yesterday and get it from off the internet. This is not an internet computer. I had to get it off the internet, transfer it onto a flash drive, and then bring it in. I think you should have thought of that when you submitted earlier. So no, you have to present it with us here, unless your advisor, I'm willing to talk with your advisor about it, and you can actually have a discussion. If he says, no, I'd like him to be able to submit his presentation now and use that, then that's fine. But as far as it goes now, unless he says otherwise, you gotta present with what you submitted. Yeah, well, you're being evaluated based on the presentation that you give on the slides you say. Yes. Okay. That's what I'm saying. Yeah, okay, but now if I allow you to do that, now say, well, here's my full presentation. If we're using the presentation that you submitted, But if I like to do that, then I can allow everybody else to. Right? And that's not the point of having this submission deadline on Monday before the presentation starts, so that people aren't working on their presentations. Okay? Yeah. So anyway, if your advisor says, no, I would like him to use what he has on his flash drive there, then we'll allow it. No, let's wait and see. Okay, yeah. And I don't know what email you sent to him, but he's not aware of it. That's what he told me this morning. Okay?
See?
Yeah. Yeah. Yeah, so if you have a spreadsheet, what's it in Excel? We'll have to verify Excel's on there, because we stipulated that all the presentations were going to be done using PowerPoint, right? Okay, and I didn't ask them to put Excel on there, I only asked them to put PowerPoint. Yeah. So, maybe, yeah, you could do that. Yeah. We'll have to look if there's Excel on there that may be a possibility. But that really should have been embedded in your presentation file, right? So. But we'll see. I don't know. We'll check.
I submitted the other course at 6 a.m. And I thought it would be the same for the presentation, but I couldn't do it. I did it until 10.
Yeah. So if he, well, he'll be back in a minute. As of this morning, when I asked him, he didn't recall getting that email, and he didn't think that we should allow. I mean, we're holding everybody to the same standard, right? It's like we're all submitting by a deadline, and so if I'm not allowing anyone else to modify their slides, then I shouldn't allow you. It's not fair to everybody else. Okay? So, like I say, unless he thinks different, there's much time now. What time we got now? So you can move. You don't need that. You can put that away. You'll use the one that's here. So, what's that? So is there any reason in your mind that we should allow you to update this presentation? We got a deadline that everybody needs to meet, right? It's not fair for us, right? So that's our position on it, is that you're going to present using the presentation that you submitted on Monday. Okay, so you can put that away.
And just in case you want to see how I would like to do that, and I show it at the end, maybe you'll let me know how I was able to do the comparison.
You don't have that in your slides?
No, because I removed the maybe 10 slides.
Well, what was happening is you were hitting the file size limit. The file size limit on Brightspace is 2 gigabytes.
Yeah, that's what I saw in your hand.
Yeah.
First submitted. I didn't check it.
Yeah, there should have been a better plan here on that. Yeah. All right, so you'll present with what's there. Do you want to do the introduction?
I didn't love it.
Okay, I'm good. Okay, so our next presenter of the morning is Alejandro Hernandez, and he will be presenting on his solar domestic hot water shoe dryer. Yes, it is. Okay.
Hello everyone, good morning. My name is Alejandro Hernandez, and my topic is a solar domestic hot water system. So this system is something new, maybe for all of you guys, because we're in a completely different career. So I decided to take advantage of free energy, like solar. So I will be talking about solar radiation and its benefits, which applies to my project. Also, I will describe it in the block diagram, an introduction, the temperature control indicator that forms part of my project, recirculation pump, dry station, and some other additional components. So before starting with a deep introduction, I would like to mention some specific points, like what are the benefits that we can get from solar radiation. Solar energy is a clean and abundant energy resource that can be used to supplement several energy needs here and everywhere. So it can also be utilized as a form of heat, such as solar water heating, and as electricity, such as solar photovoltaic. At the same time, solar water heater reduces the amount of fuel needed to heat water, because it basically captures the sunlight and uses it as renewable energy. Let's begin with my block diagram, which is pretty simple, as you can see. We start with a solid collector, which basically I wanted to emphasize in its functionality, which is heat absorption stage. That is main purpose in this project. It's going to be absorbing the heat collected from the sun. It's not going to be 24 hours, of course. It's going to be for specific time of the day. And also, it's not going to be 100% efficient. I just want to let you know, because we're going to have the same radiation at the same time. We also have the next block, the temperature control indicator, a recirculation pump, and a dry station. So this is a closed loop. It runs over and over and over. Going with the next slide, because my project is not here physically, it's installed in a shed at home. But its application can be also in a barn, can also be installed in a garage. And I would like to mention that the capacity of the system was 55 gallons. And I just used a simple formula to calculate volume, which is related to the diameters of the copper pipes that I used. I used 3 different diameters. The first one was a 1/2 inch, the second one 1.5 inches, and the third one is 7/16, which is for the drying station. So I would like to start with a video. This explains a little bit in detail what is the functionality of each of the components. Let me see if you can hear this. I think I need to turn this on, right? Should be good. for me to. Sorry about the delay, so I'm just trying to fix the sound. Okay, let's improve a little bit because it looks like the sound doesn't work pretty good. I mean, I can hear it, but I don't know why it's not working there. So basically the explanation that I'm giving in that presentation, I'm explaining that the ambient temperature is 20 Celsius degrees. And basically my project has been installed right on the roof of the shed, as you can see it. And before starting with the full description about each of the components, I am explaining the reason why I installed the solar collector on the top. And the reason is because I'm just trying to collect as much as I can radiation from the sun. So that is the main purpose. And then the next one is the solar water collector. I don't know what you're hearing. So now I'm going to start explaining in detail about the solar water collector.
The solar water collector has a dimension of 29 inches width and a height of 35 inches. The southern collector has been made by 100 to 24 inches. Copper pipe, which is 2 diameters, half inch for the vertical tubes, and inch and a half for each of the lines. At the same time, we can see that we have covered the salt water collector with plexiglass. The plexiglass has the thickness quarter of an inch, and also silicone has been applied on and around plexiglass. The purpose of this is to keep it in place and avoid heat losses, also avoid water coming inside of the water collector. Additionally, above the beach, right underneath of the copper pipe, we have the 1/8 piece of aluminum. And right at the bottom, we cannot see it. There is another isolation. This is called rigid isolation. And this one is going to help us to retain all the heat inside of this copper lines.
So this collector has 3 layers. The first one is a rigid isolation, R5. The thickness of that one is 1 inch. Then the next one is small piece of tin and aluminum. It's a combination. That one has been used to transfer the heat directly to the copper lines. So instead of collecting heat only from the copper, which is half inch, I'm collecting more by using this piece of metal.
Furthermore, I would like to include the purpose of having 2 faucets. One right on top, which is open already, and one on the bottom. The functionality of these 2 faucets, the first one, is to let the fluid get inside of the manifold, which is going to be distributed all the way down until reach at the bottom manifold. As you can see, the flow continues until the outlet of the solid collector. Now, we have an ambient temperature of 20 degrees Celsius, and we're going to check, for example, this valve.
So when I was measuring the temperature, we were getting 30 Celsius degrees. Now let's proceed to the next slide. So this is some of the steps that I took at the time of fabricating the solid water collector. These are 10 tubes, half inch each of them. This is the isolation foam that I use, which goes right at the bottom. Then we have a piece of tin or aluminum that is going to be right on the top before the copper lines. That is a frame that I built here at the shop. That's how it looks like from the top and from the bottom. After doing that assembly, I painted in black. I use high temperature paint. This is to maximize the efficiency of the collector. And I applied plexiglass right at the top. You might be wondering why I didn't use glass. So plexiglass is more efficient. Basically, it lets the light go through it better than having glass. It goes at 90% efficiency. Could be a little bit expensive, but for this purpose it worked pretty good. It has one problem, that is you can break it pretty easy. I mean, you can put small weight and you're gonna break it right away. That is not a problem. So the next step in my block diagram is the temperature control indicator and the recirculation pump, how they are linked to the process.
The temperature control indicator. The temperature control indicator has a set point. This set point was pre-established by myself.
So here, the bottom temperature is the set point that I'm talking about. And the top one is the temperature that the collector is absorbing at that time. So as I mentioned, we had an ambient temperature of 20 Celsius degrees, and the system now is absorbing 44 Celsius, and it's being transferring to the dry station.
The temperature control indicator. The temperature control indicator has a set point. This set point was pre-established by myself. So basically, when the temperature drops down under 40 Celsius, the system is going to be completely shut down. And now we have a temperature in our system, 44 Celsius. This sensor has a probe that is connected right on the top. It's right here. It's been attached to the pipe. And the fluid that is coming out of the solid collector is passing through the copper pipe. And this probe is sensing the temperature and sending the signal to the sensor. At the same time, because we have established this set point, the pump is running. You can see. You can also hear the capacity of this pump is 30 liters per minute, which is going to be the tank's description in our block diagram. The recirculation pump is the next step in our process. This recirculating pump has a capacity of 30 liters per minute. Our solid collector water has a capacity of 32 gallons. And our entire system has a capacity of 55 gallons, including the dry station. We're going to start with the description of the entire system before going to the dry station, which is going to be the last block of our diagram. As you can see here, right at the top, we have a half-inch valve and a connector right at the top. The purpose of having a connector right at the top is to connect the hose and fill the system. So, as soon as we start filling the system, the flow will go all the way down until passing our first temperature indicator. Then the flow continues, and we have a check valve, half-inch as well. The line goes all the way down until we reach our dry station. This is the dry station without any woodwork.
So that is the dry station, as I am mentioning. I didn't put any footwear at that time, just to show you what is the temperature that is getting without nothing. So at this time, we were getting 41 degrees. So basically, we were having losses of 3 degrees between the solar collector and the physical station, which is the dry station.
And the purpose of not installing any footwear is to show you the real temperature that is being dissipated from these carbon lines is reaching 42 degrees Celsius. So going back to our system, the flow comes all the way down, follows this sequence, and then goes up through the isolated pipe, reaches an expansion tank. The capacity of this expansion tank is 2.1 US gallons. The valve is already open. This is to maintain our flow.
I just want to clarify something. It's not only to maintain the flow, it's to support the system in case we have an overpressure. If we have an overpressure because of high temperature, this expansion tank has a diaphragm inside. So it's going to absorb whatever overpressure we might have in the system.
Constantly working without stopping. The flow continues through here. We have a pressure gauge. The valve is closed right at the back. Here we have a pressure relief valve. This one basically has a functionality, an important one. So as soon as we overpass the maximum temperature, which is around 100 Celsius, this is a safety device that is right on top. It's going to pop up to release all the vapor that we might have inside of the system. Again, we have some overpressure inside of the system. At the same time, this is going to help us to avoid having a lot of bubbles in the system. And this normally happens when we start the process. We continue the line, and we can see that we have another half-inch valve, which is closed. This one has been located right here, because in case that we want to drain our system, we need to turn off the pump and open this valve. So all the fluid or refrigerant is going to be drained. But when we continue with our system, the flow goes all the way up. You can see here, it's the sequence, until reached the inlet of the salt water collector. Here we have safety device in case something happens. And this is how our system looks like. Now we're going to install a pair of footwear.
Okay, now we're going to proceed to go to the last block diagram, which is a drying station.
To conclude with the last description in a block diagram, we have the drying station. This is how it looks like, dry station. I have already placed here of goods to demonstrate how it looks like. The system temperature is 44.1 Celsius with an ambient temperature in the outside of 19 Celsius. The pump is running pretty good. And at this time, we can verify it has a temperature of 65 Celsius, which means that the water is really, really, really hot.
So those 65 were not the maximum. I did a couple tests, and the maximum temperature that we were able to get with this system was 85 Celsius, which
It's
is
going up.
pretty efficient.
And today's not even a hot day, it's just 19 degrees. And the solid water collector is working pretty good. No complaints about it. Expansion time as well. And each of the components that are part of this project have been working. Excellent. As I mentioned before, the time that it's going to take to provide these shoes from the inside is going to be around an hour and a half. Might take 2 hours as much. And it's up to you if you want to keep an eye on it. But the system is pretty safe. But in case you want to increase or accelerate the drying efficiency, another device could be included right at the back of the copper loop. Be a fan. Basically, that would be a bigger project.
That would be a different project if you want to dry your shoes from the outside as well. This was based only to dry them from the inside. That's the reason why.
Because right now, everything is working according to the expected. So I don't think I would need to make any change. But just in case you want to improve your system, you can go ahead and do it. There's
So here, I basically was mentioning that you can make an improvement if you want.
another situation that I would like to let you know guys, for example, in case you would like to use this system for a different purpose, I installed a joint right here.
So the purpose of doing that is because in case you want to keep that place warm during winter, you can attach like a baseboard on it, and you can keep it warm pretty quick. Because the radiation that it was collecting at that time, it was not pretty much, but because of the size of the closed loop, which is pretty small, it has the capability to dissipate a lot of heat. It was only just with water. We can use any kind of coolant. I used one, but it didn't work because the temperature was going up twice. So every time the temperature was going up, it was opening up the relief valve. So it was not safe for me.
So the purpose of doing this is because let's say that you would like to keep this place warm, especially during winter.
Okay, let's-
Take a look.
So this is my PNID diagram. Maybe some of you guys have some idea about how this works. This is basically a piping and instrumentation diagram. And the first one is a solid collector water, and the flow starts here. Here's the fill valve. We fill the system. And you can fill the system with a maximum of, well, the range is between 10 psi to 20 psi. But if you do it from your house, you have a maximum of 75. So I didn't want to increase the psi because I don't know if I might have an overpressure in the system of the house, which is not mine. So that's why I decided to keep it running as a minimum of 20 psi. So once you fill the system, there is a temperature control indicator right beside. System go through it. There is a pump that is going to be sending the flow through a valve check. We have an indicator right here, pressure, goes forward until reaching the dry station. Then we have another pressure indicator right at the top. It goes down until reaching the expansion tank. We have the relief valve on the top, and then the cycle continues. You might be wondering how this is gonna start. So basically, the sensor, you're gonna put the set point, and let's say that you would like to have your system working at a minimum of 30 degrees to 35.
Okay, Mr. Hernandez, your time's up.
All right.
Do you have a demonstration?
Yeah, basically the demonstration is, that's what I didn't attach it, but I have all the proofs. But the demonstration is that the system was able to work above the expected, which is above the ambient temperature.
Do you have a demonstration to show?
Not in these slides.
You don't have one? Okay.
Well, the demonstration basically is the temperature that I was getting in the system. If the system were,
No, but I'm asking if you have one to show us. Everybody else had a demonstration to show.
like to see, well, for me this is the demonstration. The system is
No. I'm asking if you have a demonstration to show us. The answer is either yes or no.
Yes, this is a demonstration that the system is working properly above the ambient temperature.
Where's the demonstration?
This is a video. It's showing the thermostat is showing the temperature that is collected
This
from
is a
the.
video here?
No, it's right at the back.
Hmm?
Right here.
Didn't you already show us this video?
Excuse me?
Didn't you show this already?
Yes, I did.
As part of your presentation?
Yes. Yeah, because there's not any other way to show its functionality unless it's working.
So you want to play the video here? For the demonstration or what? They were just below that and ask questions. We'll just see it. All right, I guess we ask questions then.
Yeah.
Okay, who wants to start?
Can you bring up your P&I?
Sure.
So, you have a temperature controller, TC1, that controls the motor,
The pump. Yeah.
the pump, the motor of the pump. So, what does it do? How does it control the pump?
So it does it first through the prop that I have attached to the pipe. So the prop has an element inside which once that one detects a difference in temperature, it's gonna send an electrical.
Between what and what?
Excuse me?
There, a difference in temperature between what 2 points?
Between the temperature that I previously set in the sensor, because I could set like whatever temperature that I want to,
Okay.
but it will not start until the prop detects that the temperature has been reached. Like for
Has
example,
been reached.
yeah, like for example, if I set the set point at 30 degrees
Yep.
and the physical temperature in the water or in the pipe is not even 30 degrees,
Mhm.
it will never start.
Okay. So then it starts and it turns on your pump
Yes.
and then what?
And it keeps running the pump until we have a difference in temperature.
Okay. And how much energy does that transfer in that difference in temperature?
Okay. The difference that I was collecting with the entire system, I wrote it down here. It was 69,000 BTU per hour, and I was getting 4.4 kilowatts.
So you're getting 4.4 kilowatt.
Yeah.
How much energy is that? That's not energy, that's power. What are the units for energy? You don't have that?
And at the end, I did a test and I got 451% of efficiency. But I need to consider some tables that I didn't attach, but I have.
451%?
Yeah, it was pretty high, because basically,
Well, I guess that's high.
I supposed to dissipate more heat, but because it was pretty close. So,
Efficiency of what? Of the power going into it to the power out?
basically the heat that I was collecting from the collector. The
So
ratings.
you're collecting X number of watts of heat from the collector
Yes.
compared to what?
Compared to the temperature that I had in the wet shoes that I installed.
Because
Because
at 400% efficiency?
yeah, but it was just
How's
for
that possible?
it was just for a specific period of time because
No, but how is that possible? Think about it. How can you get 400% efficiency?
well, it was pretty high, the value that I got.
Well, I
But
guess because it's breaking the laws of thermodynamics is what it's doing.
yeah, but it's not gonna be for a long period of time. I mean, it was just for a couple seconds because the
Doesn't
sound
matter
is
how much time it is, you
No,
can't
it
do
doesn't
that.
matter. It can't be more than 100%. Unless you have an external source of energy beyond that you're not measuring.
Yeah, at the beginning I was getting 30% efficiency. And unless I choose a wrong value from a table, that would be the
That's your data.
most
your-
reasonable.
you know, which you didn't show or,
Yeah.
that would have been better than watching a videos, I can tell you that. You use the term refrigerant at one point. What is the refrigerant?
I used it at the beginning. It's called Eco Solaris, and I use it.
But is it truly a refrigerant?
No, it's really cold water. It's
Okay,
mixed-
so it's not a refrigerant then, because
No.
we'd be using it for what instead here? A
Well-
refrigerant refers to what?
I was trying. Well, I used it just to combine it with water and get more
No, I understand. To get what? What more? What were you getting more?
heat,
You sure?
especially during winter.
You sure? What's the best material, specific heat wise?
For solar collectors,
For everything. As a material, what's the best material for specific heat? What's the specific heat of a material? Let's start there.
was supposed to heat the material.
No, what's the specific heat of a material? There's a parameter called specific heat. What is the specific heat of a material? And which material has the best specific heat? When we did our analysis for hot water, when you were taking your hot water course, what is the best material to use as your heat transfer material? What's the best material you can use?
The heat transfer, copper.
No. In a hot water, domestic hot water system, what's the best material to use? In the labs you did, what material did you use that transferred the heat?
You mean like the medium that I use, water?
Yeah, you used water, okay? And water has a risk of freezing,
Mhm.
what did you do to the water?
Well, I need to combine it with
With
the refrigerant.
not a refrigerant, it's not called a refrigerant. It's glycol, that's what it is?
Well, this is a composition of glycol and
Yeah, so that glycol, what does it do to the water? It does two things. What's the first thing that it does, that we added to the water?
change its density.
Well, yeah, but we don't want that, that's probably gonna work against us, to be honest, it does work against us. What does it do? Why do we add the glycol to the water?
Just to be more reactive.
No? I don't know what that word means anyways. More explosive, is that what you're saying?
No, I mean, it will accelerate the process of increasing the temperature in the
No,
closed loop.
no, well, yeah, but that doesn't equate to what you're thinking, so. Why do we add the glycol to the water? And why in Florida, why don't they do it?
Well, because if I add glycol to the water, it's gonna be more exposed to solar radiation. It's gonna be more reactive.
No. Get rid of that word reactive, that's not a proper word for here. In a system in New Brunswick that we're gonna use year-round, we add glycol to water. If I had the same system in Florida, I wouldn't add glycol to water. Why is there, what reason is that for?
The reason is,
What happens to water in New Brunswick in winter?
gets
When I take the
freezes-
Zamboni out and I drive, what
freezes-
happens to water?
freezes,
Freezes. What happens when water freezes in a system like yours?
you just open all the pipes.
Yeah, plus it can't transfer energy, right? So we add glycol to water to prevent it from freezing. That's the first reason. The second thing that happens though is the specific heat of the glycol water mixture goes down. And what that means is we need more temperature to increase energy, the same amount of energy. Therefore, it's less efficient. Okay? It's not reactive, it's efficiency. So I can transport less heat for the amount of temperature change that I require. Okay? So it's not a refrigerant, it may be sold as a refrigerant, but it's not a refrigerant. It's an antifreeze. Okay? And by adding that antifreeze to your system, what does it do to the system? Well, it makes it less efficient.
Less.
So for you to be staying 400% or whatever, makes absolutely no sense at all. And it's definitely not because of the refrigerant.
Can you take us to the slide where you have an image of the construction of your project, of your solar collector? And don't show us any more videos, I don't want to see you.
No?
I didn't come here to watch you play videos. I wanted to see you present, okay?
Yeah.
Maybe where you were assembling it, the copper. Yeah, the upper, in the diagram, or the photo on the left,
Yes.
the upper part there that's all by itself at the top of the image, what's that part called?
Manifold?
Manifold, good. I
What's
wanted to hear you say that.
the interconnecting parts, what are they called?
What are they called?
This ones? The,
The vertical
well, no,
ones.
the connectors of these vertical pipes.
Yeah, what are they called?
Uh,
They're very specific names.
right. Radium tubes, I don't remember, what is it? The technical name for it?
Starts with an R. Ends with an R. They're called risers.
Risers.
And the back aluminum plate, what's that called?
Well, I found it as just a corner plate,
No,
just to protect
there's
it.
very, very distinct terms for this. It's called an absorber plate. Okay. And does your absorber plate have a physical connection to your riser tubes?
Yeah, they're making contact, but they're making more contact with the manifolds rather than the razors.
Don't you think it would make more sense if they contacted the riser tubes?
Yeah, I tried to do it, but it was, I was bending the pipe, so I decided to stop doing it because of the difference in diameter between the manifold and the razors.
And my next question for that is, if they are contacting them, do you think they're thermally good conductors? Is aluminum a good thermal conductor to copper?
It's not better than copper, but it will help.
Aluminum builds up an oxide on its surface, that's why it's always dull. If you shine it up, it goes back dull. You should look into the fact that whether that's a good thermal transfer or not, okay?
On that kind of similar topic perhaps of thermal transfer, you mentioned about that you had painted the copper risers and the manifolds. Specifically, what type of paint did you use?
I only selected a paint that can support high temperatures, especially above 70 Celsius.
So you said you used a high temperature paint. Was there anything specific besides the fact that it was high temperature, or was there any other properties that you maybe would have hoped for this paint would have in this application?
No, to be honest, I only looked for something that was according to the project.
Okay.
Because I had an idea that this collector could reach between 70 to 80 Celsius. So this one would be like in the middle of those parameters.
Okay, so I have a wood stove at home. Okay, should I paint your project here? Should it be painted with the same paint that I would paint my wood stove with?
No, because right at the back says the applications. Some of them are toxic, and some of them.
Well, I don't care about the toxicity. I really don't.
You just want to
If I cared about toxicity, I wouldn't sit in this room. Okay,
Yeah.
but I don't care about toxicity. I'm thinking more about the application here. Okay.
Yeah.
If I said here, Alejandro, I've got an extra can of paint that I used to paint my wood stove with, and the stove pipe and all that, and I gave it to you here, use this on your project, would that paint be the correct paint for this application? It's a high emissivity paint. Is that what you want here? Is that what you want?
No.
Do you know what I mean by high emissivity paint?
No. What do you mean with emissivity?
Emissivity means that it promotes radiation away from the object. Is that what you want here?
No.
What do you want?
I want to absorb it.
Aha. So do you think there should have been maybe some more research put into the paint? Because not any black paint is absorbent or emissive. You have to select the right type of paint, right?
Yeah, in fact, I did one test without paint, and I realized that I absorbed more heat after painting it.
Okay, so maybe by chance you may have selected the right paint, I don't know. But maybe you get better results if you actually took some time to select the right paint too. I don't know, right? And I don't know that you know, so.
Yeah.
Which is actually more important here, but anyway. Any more questions?
We're over time.
Yeah, okay. Okay, thank you.
there's no more view. Maybe like they didn't like their chocolate or
I was joking, but I think it smells like. I don't know if it is or not.
That's a little accurate.
That's okay.
That's what I think.
Okay, here's how we're gonna do this. I'm gonna walk in front, and you tell me if you see me. Yep. Well, here, let's check and see if Excel's on here, and you want to throw a.
They're on.
Didn't work.
Huh?
Didn't work.
You're on.
Yeah, okay.
Mr. Brooke,
Excel's on here, so you can, if you want to put your, Excel spreadsheet.
I have a quick question for you. Measure asking your, that's probably not.
Yeah, you can.
Interesting camera.
Yep.
what we gonna do? I know
Just 1 second.
Trying to.
I was just following up.
I will
Yeah, I gotta go to a meeting in that. Let's, I'll try to get back here like,
How you doing?
taking a breath.
dude, I was just like,
Okay, hold on, because you would think that just hitting this mute here would do, but it didn't, so I just pulled it all the way down.
Well, I just said what I heard myself say.
we're not leaving this here, right?
What? No.
We need to do.
No, it's still going.
No?
That's gotta be a bug in OBS. Because it's not even registering
How's it
anymore.
going?
Good.
What's up?
Thank you.
I guess we can measure from this what the delay is.
It's only like a couple seconds.
Is it? It's still going. That's gotta be a bug in OBS.
It's like 30 seconds at best.
It's not even registering. Yeah.
Outside is overcast. For
Yeah.
my test, I'm not sure how well it's gonna work. I may have to go to the artificial sun.
Yeah.
So I'll go ahead.
Yours is at 3:30 today?
Right, it's the last one.
Well, if you want to do it in E1011, we could do that.
E1011?
The alternate energy lab.
Yeah, I'm gonna go and see if I can
Because it's
get
supposed
the
to rain even,
artificial.
I think.
Yeah, so that would be a bummer for my partial test.
Yeah.
So I look at that possibility.
Okay. No matter what I do.
Yeah, there's something right there.
If I delete this, let's see. Remove. Are you sure you want to remove audio input capture? Yes. Oh, maybe it's,
Maybe it's a mic for this thing.
you know what it is? Maybe you don't, I was just assuming that. Maybe it's coming directly from this presentation camera wide here, which is that out.
Yeah, let's leave it like that for now, and let's go talk about the. Are you staying for lunch, or are you staying here for lunch, or are you leaving? Staying
Are
here.
you going to close the room?
All right.
Are you going to close the room?
Oh yeah. Well, the thing is, you don't have keys, so if you leave, you can't leave this place open. Let's leave it like that for now, and
No, then I'll leave.
It's gonna be a stupid thing, these uneven steps there. I saw him trip, and I trip on him all the time too.
Yeah.
Hey, so we'll see you at 1:30. We'll see you at 1:30. I don't know.
I'm wondering what.
Which mic?
It must be this.
That's feedback from over there.
Yeah.
Tap it. It's on. No, I think I heard that one.
Oh, no,
No, it is that one.
Yeah. Okay.
Isn't there not an on-off switch on that?
There is a mute button actually.
Oh, did you? Is he leaving?
Rumor has it.
Here you go. I got you.
Oh, okay, I was wondering where did
They thought you left your jacket behind.
I know. Good Thank you. I was getting kind of worried there. I don't think this is real high now.
Okay, welcome back to the symposium. And starting us off for the afternoon is Matthias Bento, and he's going to present to us his digital function generator.
Hello everyone, my name is Matheus Bento, and today I'm going to present you my SPL project. It's the digital function generator. So a quick overview of my presentation topics. I'm going to start with an introduction, then a brief overview of my project, and after that an in-depth description of it. Then I'll talk about my programming code, my PCB design and closure, my project testings, and problems and issues that I had, and then the bill of materials and conclusions, and at the end I'll do a demonstration. So what is a function generator? It's basically a device that generates an electrical waveform, and it can be in different types, frequencies, and amplitudes. It also could have offset, the offset function. It also could change the duty cycle of the square wave. So what is it used for? Typically, it's used to test electronic devices. So like in this diagram here, you have a device under test that you're gonna input a specific sine wave in it, and then you're going to analyze the output of it. So for example, you're testing an audio amplifier, and you wanna know let's say you want to see the response of it to a specific sine wave in a specific frequency, and then you can use a function generator to simulate that, and then watch the response of it using an oscilloscope or logical spectrum analyzer. So you can see that this device is very important for testing. And because of that, my project proposal was to build a digitally controlled function generator that can output the three types of waveforms, the sinusoidal, triangular, and square, with variable frequency, variable amplitude, and also has an offset function. The frequency should range from 1 Hz to 500 kHz. The amplitude should range from 0 until 20 volts peak to peak. And the offset from -5 to +5. So a brief overview of my project. I basically divided it in 5 parts. The first one is the power supply. So this part is responsible for converting the voltage from my wall adapter into 3 voltage rails, the +5 and plus and negative 15 volts. And the next part here is my microcontroller that is responsible to control the signal generation and amplification. And also it interacts with the front panel. And the front panel has is responsible to create a user interface for my project. So whoever is using it is capable of inputting values, the parameter values that they want to, the signal that is being generated. So at the front panel we have a LCD display, buttons, knobs, the on-off switch, and the signal output there. The other part is the signal generation. This part interacts with my microcontroller, so it can generate a signal with a specific frequency and mode. And after that, I have the signal amplification and offset. This part also interacts with my microcontroller to amplify the signal and add an offset to it. So basically, I'm using the microcontroller to receive the values, to interact with my components from the front panel, and based on that, I will generate a signal with specific frequency, amplitude, offset. So now I'm going to a more in-depth description of my project. First, I'm going to talk about my power supply. Here you can see the block diagram of it and also the schematic. So at the corner left, I have the wall adapter. It's AC to AC wall adapter, and it converts from the standard outlet voltage, that's 120 volts AC, to 16 volts AC. It's rated at 1 amp. After this, the wall adapter will connect to the power jack input, and then that's connected to my fuse that is rated at 1.25 amps, and then to my on-off switch that is placed on the front panel. After that, there is a voltage double circuit that is going to convert the 16 voltage AC, 16 volt AC, into a positive and negative 22.6 voltage DC. And then we have the voltage regulators. The positive 22 is going to be converted to plus 15 voltage by the LM7815, and then converted to 5 voltage by the LM7805. And the negative 22 volts is going to be converted to minus 15 volts by the LM7915. The positive 5 volts is going to be used to power my microcontroller, my LCD, my DAC, and the positive and negative 15 volts is going to be used to power my voltage, my variable gain amplifier, my op amps, and the push-pull transistors. So moving on, I'm going to talk now about my microcontroller. Here's some connections that it has. On the corner left here, I have 6 pin headers for ICSP to program the PIC. Down here I have an LED for troubleshooting. And this grid of resistors and capacitors here are the balancing circuits for my switches and my rotary encoder. The microcontroller that I chose to use is the PIC 16F18345. The reason that I chose this is its operating voltage is 5 voltage. It has 20 pins and 18 of them is IOs. It has 2 masters MSSP, that's Master Synchronous Serial Protocol. And I wanted to be able to use the SPI protocol and the I2C protocol in different pins. It also has 14 kilobytes of flash memory, and you can see in this image here that my code used 63% of it, so it came out handy. The other connection that it has is, you can see here my I2C bus with the pull-up resistors. I have here my SPI bus, and here we have a square wave enabler that I will be explaining about this later. And this here is a 6x2 header connection that is going to the front panel. The last one here is the potentiometer to adjust the LCD, the contrast. So now talking about my front panel, here you have the block diagram, the concept drawing, and the schematic. So this here is a 6x2 socket that is going to be connected to the 6x2 headers that I have in the board. And this way I can establish a connection between my main board to the front panel. The LCD that I'm using is a 20x4 LCD with I2C driver built in. I have my configuration control buttons are the setup, output, left, right, and the select switch is a built-in switch in my rotary encoder, so you just push the knob. The rotary encoder there is to increment the decrement values. I also have the on-off switch on the front and the BNC connector for the output, to output my signal. So now I'm going to talk about the signal generation part. This is my programming waveform generator. It's the AG9833. It has its own crystal oscillator of 24 megahertz, and it's connected to a voltage divider circuit. The AG9833 is a digital, it uses DTS protocol. That is a digital direct synthesis. And this is basically a combination of a counter with a DAC. So it outputs different values of voltage really fast, and with that it can produce a signal wave. It has a 3-wire aspect protocol. It can generate a signal wave up to 12.5 megahertz, and it can also produce sine waves in sinusoidal, triangular, and wave in square wave. But when it's sinusoidal and triangular, they have a 0.6 volts peak to peak of amplitude, and the square wave has 5 volts peak to peak. And this becomes a problem when you're trying to vary your amplitude. So that's why I'm using a voltage divider. I came up with this voltage divider circuit so I could change the voltage division based on the signal that I have from the MCU, that is the square wave enabler. So when I'm producing, when I'm generating the sinusoidal or triangle, they will come out of the AG9833 with 0.6 volts peak to peak, and after the voltage division, it has around 50 millivolts peak to peak. And the same thing is going to happen to the square wave, because now it's going to be generated with 5 volts peak to peak, and then it will go down to 50 millivolts peak to peak. And the reasons for that I'll be explaining a little bit later. So after that, I still need to eliminate the DC offset of the that my signal has. And for that, I'm using an active high-pass filter and the buffer after it, just for impedance matching. So now I have a signal being generator where I need DC voltages to control the gain and also for offsetting the signal. For that, I'm using the MCP4912. This is a dual-channel DAC IC. It has a 10 bits resolution, uses SPI protocol, and it can output from 0 until the reference voltage, which is 5 voltage in this case. The channel A voltage is being used to control the gain of my variable gain amplifier, and the channel B voltage is being used as the offset. So because I need the bigger range, voltage range, the 0 to 5 voltage is not enough. I'm using a negative offset against circuit for both channels. So channel A that controls the gain is going to be amplified to minus 13.9 volts to 15.6 volts. And the offset voltage is going to be, the range is going to be increased to minus 5 to plus 5 volts. So now that I have a signal being generator and now I have the DC voltage to control the gain, everything is going to the variable gain amplifier. It's LM13700. It's a current control transconductance amplifier, OTA or TOA. It has a differential inputs and linearizing diodes to attenuate the distortion. And the gain of it is gonna be varying between 0 decibels to actually 52 decibels, it's not 33. The reason I'm attenuating my voltage after it being generated by the AG9833 is because the differential input of my variable gain needs to be very low. As you can see in this graph taken from the datasheet, it's a relationship between the output distortion and the differential input voltage. So if I want a distortion less than 1% using the linearizing diodes, which I am, I need my differential input voltage must be less than 100 millivolts peak to peak. So that's why I'm attenuating my my generated signal. So it's around 50 millivolts peak to peak. So it should be theoretically around 0.1% of distortion. So now I have an amplified signal and also have my voltage, offset voltage. Now I need to sum them up. For that, I'm using an inverting summer with a gain of 1. The reasons because it's an inverting summer is that my active high-pass filter also inverts the signal. So here I'm inverting back. And after that, I have a push-pull circuit that is going to supply current to whatever load my function generator is connected to without disturbing the signal. And here I have 4 200 ohm resistors in parallel. That's a 50 ohm output resistance just for heat dissipation. And finally here I have the BNC connected to output the signal. So here is just the full block diagram and my schematic with the power supply. Here I have the MCU and the connections to the front panel. And here's the DAC IC with the waveform generator here and the high-pass filter. Here I have the amplification part with my LM13700 and the inverting summer here, the push-pull circuit. So I'm going to talk about the programming code. My code was it was made focusing on creating an interface for the user. So it's easier for them to input the values, the parameter values that they want to use with menu display. So after starting configuring everything in the code, it's going to display this main menu here. The main menu is composed by the 4 main parameters of the signal: frequency, amplitude, offset, and mode. So after this, if the setup button is pressed, it's going to the setup menu. And here you have 5 options to choose. And you can navigate through it using the rotary encoder or the left and right buttons. After selecting the parameter you want to change, you can press the select button. And if it's one of those 4 parameters and not the quit option, it's going to take you to one of these 4 menus, configuration setups. So here you have frequency, offset, amplitude, and mode. And here to change these values, you can use the right and left buttons to choose what digit you want to change, and then use the rotary encoder to increment or decrement that value. The mode here, it works similar to the setup menu. You can use the rotary encoder or the left and right buttons just to choose between those values. And once you have the desired value there, you have to press the select button to save it. If the setup button is pressed instead, you're going to go back to the setup menu without saving the value. So it says right here, if the setup button is pressed, it goes back to the setup menu. But if the select button is pressed instead, it's going to store the values in a designated variable. So while you're in the main menu or the setup menu, the output button is pressed, it is going to the the output function. It's going to call the output function, which is it's going to convert the values from the ones that you set up in the setup menu to data, and send them to the AD9833 to generate a signal with a frequency and mode, and then send the values of amplitude and the offset to the MCP for 912. So here, if the square wave was selected, if the square wave mode was selected, the square wave enable is going to be output height. So I'm going to talk about my PCB design and closure. This is my top layer. I use most of my components are SMD components, with exception of some of them. This is the bottom layer of it. And here is my printed board with the soldered components. So right here you can see my power supply circuit. After that is here's my PIC and with the ICSP. Down here we have the decoupling circuits and the header connector to the front panel. This is the potentiometer for the LCD. And here you have the dual deck IC and the negative offset and gain circuit. After that is the AD9833, the programmable waveform generator with the active high-pass filter. And here you have the LM13700 with the inverting summer. On top of it, it's the push-pull circuit. And right here you have the 5 ohms resistance, output resistance with the header to the BNC connector. That space over there is to solder the heatsink. And I divided the ground plane between digital and analog ground plane, because this part here is mostly digital, and this part here is going to be dealing with the analog signal. So for my enclosure, this is some photos of it. I have the front view here. It's 20 centimeters by 9.5 to 17.5 centimeters of length. Here you can see my LCD, the rotary encoder, the control buttons, the on and off switch, and the output signal connector. And here's the rear view of it with the input power jack. And here's a photo of the inside of it. As you can see, the heat sink is it's a big one. And right here you can see all the components of my front panel are panel mount. So I didn't have to make another PCB board just for them. And they are all connecting right here with the socket and the head 6x2 socket and 6x2 header. Here you have the connection to the BNC connector using a coaxial cable. So for the project testing, the first one that I did was a functional test, just to see if all the features that I proposed were working. So here you have the frequency. I could change the frequency from 1 kilohertz to 10 kilohertz. And here it looks the same, but if you zoom in, it's I changed the amplitude from 1 volts to 10 volts, peak to peak. And here is the offset. On the left we have 10 volts peak to peak triangular wave with a -5 offset. This is the 0 line, and this would be the -10. And here you have the same waveform, but with a +5 offset. This is the 0 line, and this is the +10. And here you can show that it produces all 3 waveforms: sinusoidal, triangle, and square wave. The other test that I did was a frequency range test. I wanted to see what would be the minimum and maximum frequency of my 3 waveforms with 2 different loads, the 50 ohms and high impedance, and also in 4 different amplitudes. So I have this table here, and I summarize it in those 4 graphs. So this column here is for the 50 ohm load, and this one is for the high impedance load. So as you can see here, they look similar, but for the sine wave, it had like a 300 kilohertz maximum in low amplitude. And when it gets bigger, it goes down to 100 kilohertz. The triangle wave had an interesting behavior, but the square wave is very poor performance with maximum of 50 kilohertz frequency. The other test that I did was the amplitude accuracy test. I wanted to see how accurate is my amplitude with the value that I input in my device to the value that I was measuring with my oscilloscope. So here's another graph to summarize that. And you can see that most of them are less than 5% of error. So it's pretty accurate. So here, the problems and issues that I have. As you could see in my frequency testing, I couldn't reach the 500 kilohertz that I proposed. Here's my sine wave when it's 500 kilohertz. It's not a sine wave anymore, it's being attenuated and it's looking like a sawtooth right now. And here's my square wave at 100 kilohertz. So it's being distortion is very high, and when I put it to 5 kilohertz, it looks exactly the same as the sine wave here. So the reasons for that to happen is the main one is my variable gain amplifier. It has a low open loop bandwidth, which means that it's attenuate all my harmonics, and almost all of them. And it also has a low slew rate, which is turning all my waveforms into sawtooth waves, and it's also creating frequency harmonics that are not present there, just adding more harmonics. That's why with my sine wave it had a sawtooth at the end. The other issue that I have is the square wave ringing. I have this peak of voltage in my rising edge and my falling edge. This was a last minute problem. Some of the possible causes for it would be strain inductance in my circuit. It could be also my power supply circuit, because I didn't have this problem with my prototype. And it could also be my signal trace path is going too close to other components, and they are interfering in my signal. So here's my bill of materials. I estimated at $400, and at the end it was half of it, like $191. So as a conclusion, the pros and cons of my project. The pros is it generates the three waveforms that I promised. All of them with variable frequency, amplitude, offset also. It has a nice menu display where you can input the values that you desire. And I would say that it has a good performance under 100 kilohertz, at least for the sinusoidal and the triangle wave. The cons is that it can reach higher frequencies. They can reach the 500 kilohertz that I proposed. And the square wave has the rigging problem. So where can it be used? It could be used in low frequency applications like audio amplifier testing and radio equipment testing. And for the square wave, in some digital circuit applications, it could be used, but if you don't have any problem with the peak voltage that you have from the rigging. So what can be improved? As it is, in software, you can add some functions to it. You can add it's not a swap, it's sweep function. You could also add impedance mode, where you can choose what impedance it's being connected to, between 50 ohms or high impedance. And you could also have a continuous output mode, where you wouldn't have to go to setup and change the values and then output a new sine wave. It would change in real time. And for the future, in the hardware, some improvements that I could have is I would replace my variable gain amplifier for a better one. but one that could handle the high frequency values. I will also replace some of my op amps, and I also retrace the signal path that I'm using in the printed board. So now for the demonstration. Turn on here, and I'm sure you guys can see it well because of the brightness. So those values here are initial values that you can use. You can just press the output button. They are going to be generated. So here I have 1 kilohertz sine wave with 1 volt peak-to-peak amplitude and 0 offset. So to change the values, you can press the setup button. It's going to take you to the setup menu. I don't know if you can see better here. So right here, to navigate between the options, you can use the rotary encoder or the left and right buttons. Let's say I want to change the frequency. I press the select button. Then I can go here and put 10 kilohertz. And then press select. So the value is now stored. And if I press the output button, we'll have 10 kilohertz here. Now I want to change the amplitude to let's say 10 volts peak to peak, and I can press output. There you go. Now I want to change the, let's add some offset to it. Let's say I want a 2 volts offset. It's going to offset my voltage, my signal wave. Now I want to see the negative one. I'm sorry, I didn't show that. Here, offset it to negative. We can do rotary encoder to change it. Output is going to offset to negative 2 volts. And now I'm going to change it to a triangle. So here you can make a triangle here. And then out through it. And here's my triangle here. Change it to a square wave. So here's my square wave with the ringing. So this is my demonstration. Thank you everybody for listening to it. Thank you.
Well, you can bring us to the schematic, I guess. Well, before you do that, what is ringing?
It's the name I found online for that.
Yeah, no, it's the correct term, but what is it? Like what is it and why is this happening?
That's what I was trying to find. I couldn't find yet.
Okay.
So I gave some possible causes for it.
Okay. Right.
It was a last minute problem that I faced, and I couldn't find the cause of it.
Maybe there's other questions while we're here. Just keep the, yeah, because maybe there's other questions about this, I don't know. The control knob, I look at that and I feel like there's a little white line there. I feel like that should be pointing to something. Is it actually pointing to something?
No. It's it shouldn't be. I shouldn't use this knob for this. I should, or at least cover it, because it's not pointed just to increase.
Yeah, because it just turns around and around.
Yeah,
Right? It's a rotary encoder, right? So
Yes.
it's not actually relative to anything.
Yeah, it's not pointing to anything.
Okay. Yeah. Any other questions on the project or the display that's being shown here?
You wanna-
Maybe we should look at the schematic then.
Okay.
Okay.
Want me to put it full screen or is it good?
Anybody have questions on the power supply?
Did you put the amperage for the fuse?
It's a 1.25 amps.
Yeah. I think if you don't have a question about this, I have a question maybe about the next slide. Oh yeah, you had mentioned about D201.
Okay.
The red LED.
Yes.
You said that you had placed it there for troubleshooting purposes.
Yes.
To troubleshoot what?
When I was soldering my PCB board, I wanted to see if I could program my PIC. So I put a blinking program.
Okay.
So now I know that it's working, and whatever problem I would have in code, I could use the LED just to indicate. So let's say the signal not being generated. I want to see where the code is going.
So the LED is blinking at what rate?
It's not blinking.
Oh, it's solid?
It's a turn off. I'm not using it.
You're not using
I was
it?
just using just to troubleshoot in case I had a problem.
Okay. So, so how do we use this troubleshooting feature? How is that troubleshooting feature used? If it's there as a troubleshooting feature, I'm trying to understand how we use that feature.
Well, let's say in your code something is not working, and you want to see until which line is it working. So you're gonna put the LED to turn on. Okay, my code goes until this line. The LED will turn on. And if it doesn't, it means that there's a problem before that. That's why I put it as this.
So it's only a troubleshooting tool for programming?
Yes.
Okay, so it doesn't actually have a like a regular use then, as far as if the
for my project.
If the project is functioning regularly, it's never going to be on.
No.
Oh, okay. That was unclear. I wasn't sure.
Yeah, sorry, it was a last-minute addition because I wanted to see if my PIC would be programmed after I soldered.
Did you have more questions on that?
Regarding the diode?
Or anything?
Yeah. Does it need to be an LED? Does
Sorry?
it need to be an LED? Is there other ways of accomplishing that other than having an LED in place?
It was the only one I thought, and it's the easy one also.
Test point?
Yeah.
Perhaps? Would have been more appropriate for that?
Could be.
Because I don't know. If let's say we didn't have you, okay? You know, you're the expert on this, okay? But if we didn't have you, and one of us was hired to service this, that'd be a question that in my mind right away is like, how come this LED never comes on? Is there a problem here somewhere, or right?
Okay.
When I see something that obviously is intended to emit light, but I don't know what it's for and it never comes on, I start asking questions, right?
Yeah.
So is it labeled it somehow anywhere on the PCB or anywhere in your documentation as to what that's for?
Oh, as I told in my report, but it would be like in the manual of my product, like to say that this LED here is used for troubleshooting.
Yeah.
And it's actually a good practice whenever you're using the MCU to put just a LED just for troubleshooting with code and whatever problems you have in your code.
It could be printed right on the PCB.
Yeah, it could.
It should,
also be
and on the
troubleshooting.
schematic too, there should be a function mentioned there, so D201 red, and then underneath that, what the function is.
Yeah.
I'm not sure what you would label it, to be honest, because I'm not exactly sure still what its purpose really is, but anyway. Any other questions on this slide? Maybe go to the next slide then. What about this one? I have a question on another slide. Anybody here? No? Okay, the next one. Oh, yeah, you had mentioned those four resistors are 417 through R420.
Mm-hmm.
You had mentioned four 200 ohm resistors in parallel to provide 50 ohm output. That makes sense to me, the 50 ohm output. Why? So what are they? Are they half watt resistors? Or
Yeah, 1 watt resistors.
They're 1 watt?
Yes.
Okay, so what's the total possible power dissipation then?
Power dissipation?
Mm-hmm. In this configuration?
Well, my wall adapter is hitting at 1 amp.
No, I mean based on the resistors that you selected. Hmm? 4 watts? Okay, so it was 4 1 watt resistors in parallel, 4 watts. So is there an advantage to going with the 4 200 ohm? Why wouldn't you go with just one 4 watt 50 ohm?
I used that for heat dissipation.
Right, but if I replaced all 4 of those 1 watt resistors with a single 50 ohm resistor that is rated for 4 watts, it would give me the same result.
Yeah.
So
it would be cheaper.
What? I'm just asking, like, what was the rationale to go with 4 200 ohm 1 watt resistors in parallel instead of one 50 ohm 4 watt resistor?
I actually didn't think about it. I'm just I'm gonna put 4 200 ohms in parallel for heat dissipation.
Okay.
And because they are spread in my PCB board, they're gonna dissipate more heat.
Yeah, I just. Is there an advantage to doing that as opposed to going with a single 4 watt 50 ohm? That's my question.
Mm-hmm.
Is there an advantage, or is it a disadvantage?
Price-wise, it would be a disadvantage.
Well, it might be. I don't know. Maybe for
Maybe they are
1
cheaper.
watts is cheaper than a single 50 ohm.
I would say a single 50 ohm with 4 watts
4 watt, I don't
is
know.
very expensive resistors in comparison with the others.
I don't know.
I was thinking about heat dissipation.
Yeah. I was just wondering if you had looked into the cost of a 4 watt 50 ohm, or
yeah,
could be higher, I suppose. You know, if you found maybe 4 watts a strange value, maybe 5 watts is more likely. I don't know, right? But did you consider that cost wise, or?
It didn't. I did.
Yeah. It would be worth looking into, especially if this was being mass produced, because if it added considerable cost to put 4 resistors instead of 1, I mean, I don't know how much of that it adds. Even if it adds $1, right?
Mm-hmm.
And you produce $1 million, that's $1 million.
Yes.
So, right? Anybody else have any questions on?
What is the maximum wattage across those?
Yeah.
Where's the maximum wattage?
Yeah, do you expect to see across those?
Yeah, that is.
Anticipated by the-
Yeah.
Let's say my load is 1 amp. That's the maximum. The heated amp for my wall adapter, and my push-pull circuit would be providing this 1 amp to my load. So that would be 1 square times or 50 watts
1 amp?
with 1 amp.
Yeah. Can the circuitry here that's you know, feeding this output supply 1 amp?
I'm not sure.
Yeah, it probably wouldn't. Most function generators that I've used don't even come close to 1 amp. So, anyway, I don't know if it needs to be even rated that high. That would be another question, right? I think that's what Mr. McGregor's question is kind of alluding to here. Is maybe there's some other cost savings that could be realized here too if we did the analysis on like how much power dissipation is really required as far as a, you know, a maximum rating here. Can we reduce that, right? Okay. Yeah. Anybody else?
My questions were on the PCB and the physical build.
Well, we can go to the PCB. Yeah. 2 minutes? Actually, no. Those 2 minutes went fast. One more question.
Okay, I was just gonna ask about your PCB. You said you divided your analog and digital grounds.
Yes.
Do they interconnect at a point?
They are connected. There's a point right here.
Okay.
This little bridge. And they're the same at the top and the bottom there.
One last question, your heat sink, how did you determine the sizing of your heat sink? You said it was quite large, but like, how did
Yeah.
you come to that?
This is actually a heat sink that I found in an old computer. And it's, I knew it would have to be big because if I ever have the rated 1 amp from my wall adapter going through my voltage regulator. So let's say the 15 voltage regulators would have from 22 to 15, 7 watts of heat. And from the 15 to 5 volts is 10 watts of heat. So that's a lot. But I didn't do any calculations for the size.
Okay.
I just knew it would have to be
It
big.
seemed pretty large, but I mean, maybe
Now you have
you
a-
need that. Nice to see calculations to
Big, sure.
go with it, yeah.
Yeah, it's a big one.
All right, that's good. I think we're
Well,
on.
we have more questions, but fortunately or unfortunately, depending on your point of view, they'll have to wait till later, right?
Thank you. Wearing a t-shirt
And she's talking about a sweatshirt. Yeah. Yeah.
I got this, but I also got
I got all of them.
I figured it out.
Well, it doesn't really matter.
You're number 18.
Oh, okay.
Have you been in We noticed it was like,
Don't say zero. You're gonna get
That's not unusual. I can
camera out and try that.
they're all mixed up.
It doesn't
Yeah,
matter.
so you're just gonna switch back and forth between the two. F5 starts the presentation. And then when you're done, you can exit PowerPoint. You're all set then?
This is how you would say it.
Is it you?
Juha. You can't, you never be able to.
Juha.
Juha.
Juha. Juha. I have to like twist my foot a certain way.
Which time did they have that?
German.
It's not far. Even my first day, I can say it right. People doesn't have Arafat.
How about if I learn Turkish?
Yeah.
But maybe I wouldn't be able to speak it. Would take on you. I don't know. Yeah.
You learn Arabic there. It's hard. I told him I'll do it, but if you're in English, I wait till next year.
Not sure when it's supposed to come.
Halfway through the presentation. I'm not carried away with that. And then I reminded you. I don't know.
Oh, I hope. I'm just reading.
At this point, we've seen everything, okay? So we can't survive.
One would hope. One would really hope. I like surprise.
Then sprinkler system goes on.
Sealed.
But this building had an upgrade. This is the trend. This is the original.
Yeah, but you know, what can I do?
All the
Otherwise, showing that 15 years. But you want me to create magic?
It's been like 70 years. NBCC. 70 years.
I think George is at the front. What? Why George is sitting in front? So I can talk to him. As in, like, I'm not going to be looking. You're presenting to everybody, not just people. Yeah, I'm glad.
Almost 70 years.
But I'm not presenting to just them, am I? Because why? I don't want to.
He just passed away. I have with me during our summer. Or summer one.
I'm just gonna
Oh, that's you know, the thing about the turkey, it's not like deep fried because the skin around the turkey kind of keeps the grease. You're not eating something that's like soaked in grease like French fries. It's actually stayed on the inside. There's a cavity that runs up through the center. The grease circulates slowly as well, so it cooks really fast. You can cut a turkey in 40 minutes compared to like 4 hours in the oven, right? 40 minutes, yeah. Yeah, but when you cut the turkey, there's no grease on the inside, but it's very moist because it's immersed the whole time, so you don't cook the moisture like you do in an oven. If you don't cover the oven properly, it will get dry. Yeah, you'll do a good job. It's the most moist turkey you've ever done. Really good. You gotta try it sometime. No, deep fried. You gotta try it. It's the best. Yeah.
You have a good baseline to be really effective. Good job. Thank you.
Did you know that we have a lunch at that No, it is.
You want to use mine? Oh, you don't? Okay.
Somebody wash this.
Use my non-initial.
Hey Dennis, take the afternoon off.
Jackets are your friend.
Oh yeah, you want to do the introduction this time? Yeah, you can do it. Yeah. Otherwise,
All right, so our next presentation today is Brian Curry presenting his solar phone charger. Go ahead.
Good afternoon, class. Good afternoon, graduating class. Hopefully we all graduate. To acknowledge my advisors, Mr. Juha. So today we're going to discuss solar phone charger that I developed for my project. We're going to start off with the introduction, the purpose of my project and why, the contents of my presentation, which includes my block diagram, my design, testing and analysis, conclusions, limitations, and recommendations. So let's start off with why I chose this project. Now, I'm from Jamaica. As most people should know, it's a very tropical place, sunshine everywhere. I love the sunshine. My good friend George can attest to that. We're like plants, we need it. And I also live on my cell phone. Now I can speak for myself. I'm on my phone 24/7, given the chance. So I said, why not include something that I love and put it together. I also travel a lot, and going around, it's pretty annoying trying to find a charging port. So that is also one of the reasons why I said a phone charger. Now, yes, you can call it like power banks are there, but when your power bank's dead, unless you have a source close enough, you can't charge it. So I said, might as well implement sunshine, solar power. It's green, it's good, to develop my project. So that is why I chose a solar phone charger for my project. Now let's go into standards. Now, there are set of standards that govern wireless charging. My project will not meet this, as the standards are very high to attain, and there's a lot of testing and everything that goes through for it. So, the QI standards, as I said, are standards that govern wireless charging, which includes resonant inductive coupling, which is charging at resonant frequency, which is efficient over a short distance, frequency and power level, which charging a phone would require 100 to 250 kilohertz or 6.87 megahertz. Communication protocol, which all QI chargers must interface between transmitter and receiver to communicate, which would monitor to say that yes, the device is charging. Safety and efficiency, which they have foreign object detection, so non-compatible devices cannot be able to charge, and thermal protection, and alignment and tolerance, which gives flexibility. As you know, chargers, like no matter where you place your phone on a specific port, you will still be able to charge your device. Let's go into my block diagram. As you can see, the dark arrows with in-use are in-use charge voltage that's being induced. So I'll be taking sunlight from my PV panels, converting it to electrical energy, charging to my battery charger IC, which would regulate charge to my battery. My battery will be supplying my wireless transmitter circuit and a voltage regulator to allow me to have wired charging. I chose wired charging also just in case not all phones support wireless charging. So you may have a phone that requires you to have wires. So that is why I implement wired charging in this project. So here we look at my concept, design concept. So you can see my solar panels. I have LED indicators for charging and not charging. There's a rocker switch to enable wireless charging. The side view, which will bring off my USB, and the front view just for connecting my transmitter cord. So let's take a view of my schematic. Now I should point out there are some errors, so bear with me if they come up or not. Yeah. So let's go into the battery charging circuit. So here we have the battery charging circuit. So the diode here is for protection, just in case of over voltage to protect my panels. I have a voltage divider here between R1 and P1. The use of P1 now is to set that voltage needed to turn on my transistor for charging. R2 here is here to limit the current for the base for biasing my transistor. I have D2 for protection of my transistor, as without D2, due to the spike of when my transistor will turn off as our inductor behaves, it would cause a spike across my transistor, and there is a certain voltage range that it would operate. It will cause a damage there. So in the charging cycle, current will be flowing through to my normally closed contact, going through my green LED would indicate that there is charging available. I have a diode here for protection of not my battery, so it cannot backfeed into the circuit causing damage. A resistor is just to dissipate that current to protect my diodes, and D4 is the red indicator to determine that it's not charging. So let's look at the next section. As you can see, it says wired charging. It should be wireless. So I have a switch in place, because as I said, we're taking supply from the battery. There's a switch in place going through, which would enable my transmitter coil that would be connected at J3. One end will be connected here, and that transmitter coil is center tap. The center tap will be connected at 2, and the other end at 3. One would be going to be connected to my gate of my MOSFET, which C4, C6, and C5 are just for voltage stability. The other end of my transmitter coil is connected to C7, which would enable my circuit to produce resonant frequency. As resonant frequency is very important in charging. Without C7, there will be a waste of all that energy, all that AC signal to be going across. So my MOSFET here is for converting my DC signal to AC, as I'm getting supply from a battery, and you cannot transmit DC signal. You need AC to be charged. You need a magnetic field that's collapsing and to induce voltage with the receiver coil. So yeah, go back. The next section here that I'd like to address is the wire charging. So I have here my battery supplying my capacitor, which is in place at my voltage regulator C-in, which is a bypass capacitor. It is 10 microfarads. Is that, based on the spec sheet, that's adequate enough to filter out, well, for provide stability, that is. C3 is my I have C3 there to C3 here is for stability at the voltage regulator for frequency compensation. And its power is being going to supply a USB-A port. I'm not using the differential D plus or D minus because that's for data transfer. Because I had to upsize my battery because of the dropout voltage. Originally it was 5 volts, and due to the dropout of my regulator, I had to bring up my battery voltage, or else it would have not regulated to the 5 volts that I needed. I had to implement a receiver circuit here because I was not able to transmit power directly to my phone, and I suspect that was due to not achieving resonant frequency as desired. So for the coils that I built, I needed to implement a receiver circuit which is similar to what is in your phone. So for how robust my coils were wounded, I decided that I needed for this to show any charging. I built a receiver circuit here, which just a full bridge rectifier. I have a smoothing capacitor here, C8, C9, and C10. My bypass capacitor for stability, and C10, as I said, is for frequency compensation, and that would be going to, once again, another USB port, just to simulate what would actually happen if I place my phone directly on the coils for power transfer. Next up, we have the PC design. Now, doing this was pretty new to me. I've never done a PC before. Thanks to Mr. Ligier for his help there, because I had quite a challenge in printing, and Mr. Metcalf. So I didn't know that at the time to switch the ground plane at the bottom. So I had a lot of issues, especially with my circuit at the time, as it wasn't correct. So I had some issues there with PCB. Going forward, now I know how to tackle that. So mounting like my relay, my terminal blocks was quite an issue. Now on to testing. There were 2 tests that were conducted for my project, which is the time of charging for my batteries, as you'd like to know how long it takes to charge a battery, and the efficiency of wireless transmission. For my battery test though, I was not able to carry out this test as I had minor issues with the circuit, and at the time of fixing, weather came in, there was rain, so I had limitations there, but I did have a sample calculation of what was my expected theory of how long it would take to charge my batteries. Here's the table. Could not fill it out. And as I said, the second test was the efficiency test, which I would take the power going out versus the power in to determine how efficient, so to say my project is not as wasteful as it's transferring energy. Here is another mistake, as the current should be in amps and not milliamps for in. So an example of expected where I had 300 milliamps, for example, and you divide it in to your battery capacity, and it would take 8.66 hours. Now, for me, that's not really practical, because I'm not going to sit out there, have my project out in the sun for so many hours. You wouldn't be able to use it. And the efficiency, as I said, due to the error, would have been 4%. Now, for me, that is also very, very bad, as I said, but I think I was not able to charge it due to not occurring resonant frequency between my circuit. So to conclude, it can be concluded that charging I'm capable of charging the phone battery safely, and it's an auto cut-off feature, so I won't need to overcharge my batteries. Wireless transmission is possible, though I cannot place my phone directly on my coils to transfer power, but using a receiver circuit that I built, I am able to do it. Now, limitations that I have experienced during this project, and it gave me quite some challenge, were the design of my coils. At the start of it, taking a project from the source, I did not think there would be so much design into diameter, the length, the number of turns, because I'm trying to achieve resonant frequency, and that is something that you should take into accountability, as resonant frequency would limit all that extra waste and everything would be going directly across to your phone. So going forward, or from learning from this project, my coil design is something that, to a commercial coil, which is something like this, versus the coils I built, not even in the phones, they're much smaller. So I realized that was a big issue, and probably one of the reasons why I could not have achieved direct charging. I achieved it once, and that was about it. So yeah, going forward, coil design, as in the number of turns, I didn't take that into consideration until much after. So that I feel would have made my project much more better and much more efficient. As I said, having the circuit run at resonant frequencies is very crucial. Next, weather conditions was another. I could not carry out my testing. I would have loved to carry it out to know how long, but just based on some sample calculations, I could kind of get a rounded value, and still I was not appreciative of that, because, as I said, I'm not waiting 8.6 hours or 9 hours to charge my phone. For that, I would have loved, as I said, on recommendations though, I'd implement a battery charging IC to charge my batteries. At the start, that was what I chose, but due to mounting issues, I was not able to carry out using that battery charger IC, so I had to redevelop a different approach, and that is how I came to having the battery charger circuit that I have now. It's an auto cut-off one, so it saves me from standing there waiting to see my batteries to completely charge. So what would have happened is, once at full charge, it cuts off automatically, red indicator, so I know, okay, I'm good to move with my project, because portability was one of the most important things. I would also use a transmitter coil, a commercial transmitter coil, trying my best to have it run at resonance frequency instead of designing one, because the design considerations are not as easily done, as I've made so many coils. Thankfully NBCC has a large amount of wires, or else my pockets would have been crying. Pretty much I was very thankful to at least get something out of the project, as it took quite a lot of time. And time is not something that we always have. So that would conclude the end of my project. So here the demonstration. I'm only able to showcase the wired and charging. So I really don't have any lights to showcase the battery charging status, but as you can see here,
You can't see it.
Okay. We can't see.
No, the projectors.
Oh.
So as you can see here, my phone is currently charging, 5 hours and 5 minutes until full charge. For my battery charging, there's not much sunlight in here, but if I use my artificial sunlight from my phone, as you can see, it's showing the charging status. Up. So this would indicate my battery is charging. The switch here would have used to enable my wireless charging. I feel like damage the MOSFET there, so I'm not able to transmit any power at this moment. But yeah, that would conclude my presentation of my project. So as you can see, the battery is charging. So
Anybody have questions on the project itself before we? Yeah. Okay, I guess nobody has questions on the actual project, so we'll go to the.
Well, when you were doing the demonstration, your phone was connected to the,
It was plugged in, right?
plugged into
USB.
the USB port?
Yeah.
You were saying the wireless transfer is not.
Yeah, it's not.
Okay.
What about the schematic then?
Yeah.
Yeah, take us to the schematic. Maybe, yeah, right there, that one, we can start there. You mentioned that, you mentioned that D1 provided over voltage protection. Can you explain how D1 provides over voltage protection?
Just in case there is any damage in my circuit, it would stop anything from going back to my panel, so it wouldn't damage my panels.
Is that over voltage protection?
But from any excess current, that is, from damaging it.
So it stops current?
Yeah.
Yeah. So it stops current from flowing from where to where?
It would stop current from flowing, just in case there's any fault, failure or anything, it would stop current from going back to my panels.
Is it if there's a failure?
A short or something caused.
What condition would cause voltage to flow from, because your goal is to cause voltage doesn't flow.
Current to flow.
Your goal here is to cause power transfer, right, from the panels into the battery. Is that what your goal is?
Yes, that is.
Okay. And so, what condition might cause power flow to be in the reverse direction?
I have D5 there protected in case of the battery, so I guess I'll probably have failure in my relay.
No, I'm not even thinking about failure. What condition might cause power to flow the opposite way?
Probably failure from my panel.
I'm assuming that the phone probably has something to do to prevent that, but I mean, you're showing here a battery. Is that the phone battery or is that the battery in your
Yes, the
circuit?
batteries.
Oh, okay. So
The phone battery.
you got a battery in your is part of your project. What condition could cause reverse power flow from the battery back to the panel?
From, well, if my batteries are fully charged,
Yeah.
I have a diode in protection there to stop the battery from going back.
Okay, so maybe that's what D5 is for,
Yeah.
right? D5, so D5 is to prevent what?
That would be over.
Ah,
D5 is to protect my battery from going back in the opposite.
from discharging where?
Into my circuit.
Back through into the circuit. And what would cause there to be a lower potential towards the left of your circuit than at the right side where the battery is? Because you talked about it during your presentation. But I wanted to hear it here.
If my transistor,
In fact, you mentioned that there isn't much solar energy in this room right now, right?
not having anything from my panels going forward.
So what if it's dark?
Yeah. Then
You don't want the current going back to the panel, and the panel basically shorting out the circuit, or drawing current. And the panel should always be providing current to the circuit, not acting as a load, right? So, I mean, I guess D5 would provide that feature. Okay, so your battery doesn't discharge. And if that's what D5 is for, then what's D1 for?
Well, at the time I thought I was protecting the solar panels having D1 there.
Think of it the other way.
Maybe it's the other way, yeah.
Maybe you're protecting your circuit from your solar panels.
Yeah. And I see you have a terminal block there, right? Is there something special about that terminal block? Or is it just...
No, it's fine. This is just to connect to the circuit.
So it's two terminals that are exactly the same on that terminal block, right? Is there anything preventing the solar panel from maybe being connected incorrectly somehow?
No, I don't have anything.
Okay, so what's D1 for?
At the time I thought it was protection for my panels.
Protection from what though?
From anything going back the other way.
I think that, like Mr. Metcalf said, you need to think it from a different perspective here.
Pin 1, what connects to pin 1?
Yeah.
and J1?
I'm trying not to.
What connects to pin 1?
What connects to pin 1?
That would be the power, the positive part.
Oh, the positive, okay.
And pin 2 gets the negative?
Yeah.
Are you sure that's always going to happen though?
Is there anything preventing that from being interchanged?
What happens if I go in there and I don't have my glasses and it's dim and I'm the old me and turn them around?
There's not enough sunlight so we can see.
Yeah.
What happens?
And then that protection, if you interchange the pins and you have positive at 2 and negative at the ground, and then the diode would stop anything from coming back.
No, it's going that way.
It's going that
Energy
way.
goes that way. If you reverse the wires on J1 by mistake, what's going to happen?
Power is going to be flowing in the other direction.
What's going to flow?
Current is going to flow in the other direction.
And therefore, what's going to happen?
Then it will cause a damage to my circuit
Why will current flow the other direction?
because of how it's connected. So the positive it will flow in the conventional current flow, so it will flow from positive, negative, going back around.
Get it?
Yeah, I grasp it.
You talked about this coil that you spent so much time and effort building, and then you mentioned that, you know, there are commercially available coils. Why didn't you just buy the coil?
I did.
Well, I guess that part wasn't obvious.
I did, but because of center tapping, I wanted to center tap the coils, so at the time I wasn't sure of any other way to develop this, so I said, I had a proposed circuit that would have had 2 MOSFETs doing my switching and everything, but I tried that and it failed, so I redesigned it and realized that I had to develop my own coils. So that's why I went ahead and mounted so many, trying to get the correct turn ratio and trying to bring it to resonant frequency with my capacitor. Trying to get, it was after that I realized, oh, I need to take into consideration like number of turns, the length, and all of that, and I still was not able, I feel like it wasn't working due to not performing at resonant frequency. As we got it once, we charged Mr. Juha's phone once, and never again. So I redesigned it just to work, just for functionality purposes, to simulate what would have actually happened, and that is why I went with a receiver circuit to at least give me something.
Has your phone charged since?
It did.
When it's plugged in.
Uh,
Any other?
I have a question.
Yeah.
Can you go to your transmitter something? You mentioned what is C74?
Resonant frequency between the inductor and my capacitor.
So how did you come up with the value for C7?
Well,
what is your inductor
I
size?
took it from the source at the time.
Yeah.
So then I realized if I have the known value of the capacitor and I know what resonant frequency I'm trying to oscillate at,
yeah,
transposing that formula, you get some value of L.
Were you able to calculate L at some point?
Yes, I did. But still, wounding these, I did not get that enough inductance that was needed to transpose that formula now to get the number of turns, the correct number of turns. So I tried to go with what was designed from the source itself, which I still did not get the circuit to oscillate or to run at resonant frequency. And I realized just from the QI standards that it is crucial to have that, or else you're wasting all that energy. As you can see, my conclusion was at 4% versus a wireless charger that is 75 to 80%. So that efficiency was very bad, very wasteful. So practically, doing this again, which I love to because it's a nice project for what I would have went with commercial coils, redesigned it, and done it much better, given time and understanding.
You said you're not going to stand in your, I think, in your test results. You're not going to stay to charge the phone for 8 hours.
No,
and you ask us to buy your product. What could you
I would
do
need to
make it?
upsize my panels, and then that would, for that current, and then that would still
upsize
or buy bigger panels, and then that would still, because you need that charge current. For my batteries, for example, from the spec sheet.
What's the power that those panels can do?
2.5 watts.
What?
2.5 watts.
Each panel?
This is one panel.
Just one panel.
Yeah. So you'd need, and then that would, having a bigger panel would remove it from having that portability of what I set out.
If you go to the results, just go to the test results. One more. Yeah. How come you got 3.7 watts?
Power out. And
That's power in.
I put 3.7 watts going into my circuit.
You just told us that your panel is only 2.5 watts.
My panels have nothing to do with supplying power. That's my batteries. It's charging the batteries, and then the battery will be used to supply the wire charging and
Yeah. Sorry.
Which just means it takes a lot longer to charge the batteries.
Yeah.
and practically, as I said, I'm an outdoor person.
You might go with an oversized PV.
And then that would reduce of having that portability, then it pretty much makes sense.
But it's going to increase the cost.
So if those calculations have been done at the start, what's your conclusion then?
Conclusion, if you can charge, it's gonna take a long time to charge, but practically it's not feasible. And then if you go with bigger panels, that's more of a cost thing, so producing something like this would. So for a niche product, it's nice, but luckily, I implement going forward, I'd have the batteries removable. If you need just something and an extra booster, that's when I'd really implement the solar. But currently, for me, I'm not sitting that much hours or leaving my product out, especially where I'm from. You never come back and see it. So I'm not leaving my product out.
It's not just it's everyone.
You can buy, but I'm not using it.
Yeah. Any other questions? Came in, schematic, yeah.
I had a question on Q2.
You too.
You mentioned Q2 produces your AC signal for your...
It would allow me to convert DC to AC, yes.
So, can you explain how it produces an AC signal and what kind of frequency you produce?
I can't say I know the switching speed of the MOSFET there, but during the on cycle, my MOSFET will be on, allowing flow of current, so I have the voltage doing on and off, so it will be fluctuating on and off, giving me that pulsating signal, which that generated my AC signal.
What make it switch?
Yeah, which components set up the switching part?
The gate of, so R4 will allow that, and so because it's gate triggered by voltage, so having
Just R4? Is R4 like switching the gate on and off?
yeah, that's what I like.
A resistor
Well,
can perform switching action?
no, but it limit my current and charging of my capacity.
Because something has to be pulsing the gate there, right? So how's that happen?
My capacitor will be
Which one? I see four of them
C5.
there.
Just the capacitor?
Kind of a circuit is it overall?
What's on the terminals there?
terminal block.
What's on the other side of that?
It would have been my transmitter coil.
So, coil? It's another word for coil.
Inductor. So charging and discharging.
Well, it's got more, it has more than just that to do. If you look at it, that inductor inductors. What else you have? You have a series of capacitors and a resistor. Does that remind you of any kind of circuit you saw in first year? Resistor, capacitor, inductor.
RLC circuit.
So what's another name for an RLC circuit? Especially when they're in parallel.
Some you saw in AC circuits.
Starts with a T. Ends with a K. There's an N in the middle.
My brain is kind of...
Put all four letters together and you get it.
T-A-N-K.
A tank?
Tank circuit. So what does a tank circuit do? A word that you use several times. Tank circuit, what does it do?
Resonant frequency.
It resonates, exactly. So the combination of all that energy being exchanged between, especially the R and the L, right, causes a switching action. And you got two tank circuits working one against the other. So you get that switching happening, that exchange of energy back and forth, back and forth. It goes from DC to
AC.
basic first year AC. Wasn't a hurdle, it's a building block, right?
That's true.
So what's the frequency of that gate drive then?
I think at the time it was oscillating at like 39 kilohertz.
Did you measure that value?
Based on calculation for what I had.
You didn't measure it, you didn't take a scope and take a lower measure?
Time, no, I didn't cross my mind. 'Cause once I realized I wasn't able to charge the phone, I figured I was not at resonant frequency, so I needed to do something to get as close to that value as possible. So at the time I didn't think about it.
Did you know if it oscillated at all?
Yeah, I was able to.
What happens if it was oscillating at 70 kilohertz?
I don't think I still would be able to charge a phone.
I'm not saying you could or couldn't, but what happens if it was, you don't know.
It would have been nice to know that. Maybe that would
If it
have
was
solved your problem if you knew that.
If it wasn't oscillating, it would never charge your phone. If it was oscillating at a higher frequency or a lower frequency, then you can look at changing things to shift that resonant frequency around. Basic troubleshooting. If it's not oscillating, well, nothing you can do if it was oscillating. Will transfer energy, right? I've got another question. You decide to, at the start, said you decided to ignore the Chi standard. Why did you decide to ignore that? Considering all your phones and that, you're more likely to follow that standard.
Because of how complex it was at the time, there's a certain level of standards, and at the time of designing, I didn't think I would have met those standards, other than trying to have the circuit resonate at a resonant frequency by communication between, I would have done between like a microcontroller or whatever. So I personally, there's a set of standards, and I checked them out, and I realized I wasn't going to meet that. So to put that
I
there,
don't
just
think you necessarily had to meet them, but you could have used them as a reference to get functionality. So you, at that point, you would know what the resonant frequency needs to be, how much, how the phone itself is going to respond to the stimulus for it to want to start charging, things like that. Whereas here, you basically just, it's the gunshot. You can't just load the gun, fire it, and hope, see what lands, right?
But you can see there's a lot of targets there. So, you know, I don't think anybody expected you to have a Qi certified battery charger, but it would have been a good start of
A reference point going forward. As I said, it's something I'd still want to get done. So it's pretty interesting. So maybe if you have some time there, Mr. Metcalf.
I got no time, but I got Chris a whole bunch of bullets. Nothing's done yet.
Okay. Thanks for the time. You're out of time too.
Oh, thank you.
Yeah.
Just quickly for 10 minutes. Jonathan? Jed? Mateos? Louis is here, the other Louis? Nathan? Adam? Paul's here, yeah. Justin? Ryan is here. Ashley? Joel? Jose? Or no, Jose, sorry. Both of you. Oh, that's great. Nevin is here. Aljon? Dearford?
There are 2 days. Because
Claudio?
an extra day.
Yeah, makes sense.
Put 2 on the last day.
Yamaju? Daniela?
So it's easy to save or I figured.
Haley?
Why go all of the shade?
Just stepped out.
I agree.
Juan? Jake?
Digest this.
No, without you. George?
He was sitting right here. Yeah, he's up next.
Yeah, he does.
Right here. He'll lose more than attendance marks, right?
Guillermo?
Yes, sir. Yes.
Benjamin? Jose is here. Marisol? Gilbert? Here. Antonio? And those I didn't name, I saw you in some form or another, so. Is that Pete here? Yeah.
One day I went to talk to him. Sit on that line.
Okay, so you got the boys. Alright.
Did you You're taking off? Oh, wow. You're coming back? Yeah. You're taking off? You weren't the prankster that played that Black Goose prank on me? That wasn't you?
Yeah, this.
I thought it was you.
Yeah, this stuff that looked like.
It looks like that slime that you buy out of the.
Yeah, let it sit there, it's really black, oily, and it would just make this pool, and you put it across.
I thought it was you.
Yeah.
It could have been. Maybe you were just.
I was a participant.
Oh, you remember that? I remember
the
scope, I think it was.
I remember you guys were all working in the lab. You know, I was working on a PLC, and there was a computer programming device on the PLC, and they were working. I had my back to them, and then something got my attention. I had to go to the office or something. And when I came back, I started sitting there again, and they were all working. Oh, okay, they're all independently working. And then I looked, and I'm like, no, like that, and then they all started laughing at me. I was pretty sure you were responsible for that. Don't think it was It's not a bad thing.
I would be proud of that.
Well, I always associated with you, and that's the reason I always remember you.
If that works, even that works.
Yeah. But maybe it was one of your classmates. Yeah.
Who's your class?
Matt was boys.
Yeah. Was that the year we had? That was the big year. That was the year we had 16 people.
There were 11 of us.
Yeah. Because there was 16 in the lab. I remember trying to juggle the lab. Remember we tried like, well,
because
we do this one and two.
those lab
we only had like limited.
one at a time.
We had 2 or 1 or whatever.
It brought back so many memories. When you asked what's the drop?
Yeah, I got my question. Yeah.
I know. You get up there and everything.
Oh yeah. That's why I
He was
wrote.
remembering all the answers. I was like,
That's why when I was doing the intro, I wrote your names down so I wouldn't forget. Because it happens, right? You're standing in front of, oh, what's their names again? As well as I know them. You know, it's just you blank. Yeah. So it is the way it is.
Come back tomorrow.
You do. Well, it's always Monday and Tuesday.
They've been double booking us all week already.
The same as us.
Yeah.
I'm going to be away next week.
Oh, okay. Yeah. Well, we're glad that you're able to attend for the time that you could.
Fridays are supposed to be like nothing, but then every ad hoc meeting are like, oh, there's nothing on Friday.
Yeah.
So like Friday's always like stacked with like.
That's our Wednesday afternoon. They don't allow us to have classes or whatever, but there's always, everything just piles up there.
Yeah.
Alright,
Well, send some other people tomorrow or next week if they can come. If they're not too busy.
Yeah, next week probably tomorrow. Next week.
Sure. It'd be great to have them.
We get less people to pop in because of the streams.
Maybe we should stop the stream.
Are there like lawyers?
Oh yeah. Yeah. Well, last year they gave us some feedback and said, yeah, we were following along. And you know, it's kind of a double-edged sword because you want to have the stream available for people who you know they're not going to make it anyway. Some of the employers in Nova Scotia, whatever, and and they probably wouldn't make the trip anyway. But then it's like, I wonder how many people like would have come in person if the screen wasn't available. Get Andrew to come, yeah. That'd be great. Yeah. Right. Oh yeah, we still have it.
Yeah, totally. Don't work though. You know what? It's the keyboards. Because he had bit bashed the keyboards and PS2 keyboards are pretty rare. But now we try to use the other ones.
With an adapter.
With an adapter, it doesn't work. And the PS2 ones, they don't, and not all of them work. And we lost the original.
Oh yeah, that's right.
I was going to
You could probably bring them PS2 keyboard.
Yeah, we just have a big stash we got rid of it.
We still have,
What we need to do is just get a stack of them and try them.
Yeah. Really what should happen is that should be Thursday.
Yeah.
But I think that it's less impressive nowadays. Not like his, but people. Oh, yeah. Wow factors.
Yes. Yeah, because back then we weren't using our phones for that.
No, exactly.
We had flip phones. Yeah.
But it also records it, right?
It's recorded. You can watch it later if you want. Yeah. No, it's being live streamed and the recording is retained on our YouTube channel.
If you guys end up having somebody
Yeah, you could. Yeah. So just if you can't get access to it for some reason, just send me a message or text me or email me, whatever, and I'll look into it for you.
All right, gotcha.
You sure you know
Right.
Yeah, you could. I get some.
Okay.
Send us a posting on, we'll put it on the.
Yeah, I'm still part of the group. You can add yourself. Yeah.
Will do.
And don't be shy to reach out to us with any questions you have about anybody. We would rather take the time to have that conversation than to have you.
Well, you've never seen me something like that.
We've heard about those things
I can do
See you later. Yeah, no problem.
In the absence of.
A permit. Oh.
What really makes that happen?
Go the other way too. Make a big
Take it back.
Stand up.
That's most of the
We're gonna demonstrate right here. Makes it easier. Oh yeah. No, we were talking about going down to E10. But if you're gonna do it here, then yeah.
There's another reason for
Okay, well, we'll find out. It's a surprise. It's a surprise.
Well, you can help us bring them back down.
It's not working well. We're only like a reason is that this happens today.
For the last one, it's gonna go stand up.
No, it's gonna happen. Yeah.
Oh, you mean we can get people to help carry it? No, you can do that. That's what I think.
Where it's like
to run upstairs.
People waiting for you. That's available. So it's not as
Yeah, he was in my class, and then his project involved, we had an applied research lab involved. And it's funny because afterwards he got hired to continue the project upstairs. I asked him one day, what's the difference between here and your project? I remember he said, I don't know if you know, he says, here we can back deadlines up, there like we could.
You see where he's like there? It shows up on here too, so we can see, right? So, are you using this?
Exactly. I'm going to use it.
Oh, you are. Yeah. So then if you do that, you're just gonna say you're on your slide. You're just gonna exit the slideshow. And just wait for this. So you're gonna click on the
low risk.
Exactly.
You know what I mean? Not consequence.
Okay, yeah, it's not on, yeah. We only do the instruction. We get Christy, what you want to do? You do want to? Okay. You can do it, sure. Just, what do I say? This is George Palmer, and he's gonna. I get to introduce you.
Oh, wow.
There we go. Right off the screen. Yeah.
Welcome to our last session for today, and I would like to introduce Mr. I'm looking at a PowerPoint, I should Mr. George Palmer, and he's going to be talking about a temperature controlled solar air heater. So, looking forward to it.
Thank you. Good afternoon. I said good afternoon, guys. I should be the one who is. I don't understand this. Okay, my name is George Palmer, and today I'm seem as if everybody's cold, so hopefully I can warm you up with my temperature control solar air heater. I didn't really plan this. Brian really used the Jamaican line, so now I'm struggling. I'm at a struggle now to find an original line. I had it written down here, and I don't know what to say anymore. But anyway, I'm from a tropical country, and from I've been here, I've been struggling with the cold. The cold has been, sometimes it has been depressing. I've only read about these kinds of temperatures. So from day one I was there, contemplating, thinking, even with my wife saying, what can I do to warm up this place, man? I'm a student, so turning on the heat is not one of my favorite things because it shows on the utility bills. So I've always been researching and looking at options as to what I can do to help with that warming up process. And I've been looking at solar air heating from before SPL. I was thinking of doing one of those do-it-yourself projects to make one. I even thought of using the pop can kind of thing. So when SPL came along and the idea was thrown out, I immediately grasped it. In Jamaica we say, I use one stone and I kill two birds. I don't know if you understand what that means, but I get to achieve two things with one hit. So that's the reason why I chose to go this option. Solar air heating has been around for a very long time. From before any of us here was born, there was always been using solar to dry things, especially in the field of agriculture. But nowadays it has spread now into a whole myriad of different areas. They have got more sophisticated with the heating techniques and the technologies that are applied. And in essence, the solar heater, what it does, it just harnesses the sun's energy and it uses it
it converts that energy into what I call usable heat. And it has many different applications. And they're broadly classified in two groups. You can have in the active or the passive groups. The only thing that separates them is the fact that the active group uses forced ventilation. And my project here represents one of the active loop, and it has forced ventilation, but we go into that a little bit further. They can offer significant savings as they complement traditional heating techniques. And what I'm trying to do is not to replace traditional heating, because there are limitations with solar and solar technology. But what I'm doing is complementing it, and you can save a lot of money in doing so. In addition to that, I'm an environmentalist, so anything that is on the green side, I'm on that side. Not only the money side, but also on the environmentalist side. So for me, it was a no-brainer. Solar air heater, that's my project, and that is what I am proud to present to you today. The objective of my project was to develop a temperature control solar air heater system that utilizes renewable energy, in this case the sun, for heating purpose. It also has a component an electronic control component that will allow the heater only to operate if the outdoor temperature is higher than the space that is being heated. If the converse happens, then the heater should shut down. And it was also to test and validate the efficiency and the performance of the heater. Now let's talk a bit about how this happens. What in that box there, what happens really when the radiation goes into the box. Now, oops, sorry, let me just go back here a second. Yeah, technology, I'm just, yeah. All right, now we have the sun here, and the sun, of course, shines, sends its rays down. Some will diffuse through clouds, some will be reflected all over the place. And it will go through what we call a glass or a glazing. In fact, what I should explain is that you have three main sections on any solar air heater. You have a glazing area, you have an absorber plate, and you have what we call a insulation that isolates or insulates the inside component from the outside environment. The absorber plate primary function is to absorb the heat, and as the cold air passes over, there is a heat transfer from the absorber plate to the cold air, and the air leaves the unit being warmer. There is a glass or glazing, and it plays a very important role, is that it allows sunlight to penetrate or to be transmitted easily inside the heater, and it also does another thing. It doesn't allow those radiation to escape that easily. It's almost like a trap. You get in, I'm not letting you out. So while it's inside there, heat is transferred into absorber plate that is usually painted with a dark, flat color with high emissivity paint. That word always gets me. And because of that nature, it is really, the nature of the paint is that it readily gives up whatever radiation it absorbs. So that will help with the heat transfer process. And as I mentioned, everything is now enclosed into a wooden block. Well, let's talk about the system overview of my system here. Now, there are two sides to the system. that I designed and built. There is the absorber side, the solar heater side, which is this section here, and over on that side is the control side of the electronic control that controls the on and off operation of the fan. On the heater side, it's simply two fans, an inlet and an outlet fan, that forces air across the absorber plates, and then the air would exit being hotter than how it entered. Additionally, there's a sensor that's placed on the outlet side of the fan, and an inlet sensor that is mounted on the PCB of the controller. And their primary function is to sense the inlet and the outlet temperature, and they are arranged in a voltage divider configuration, and we'll get into that a little bit later as we look at the schematic. And as you can see here, because of the voltage divider configuration between the inlet and the outlet sensor, there is what we call a junction voltage that would be seen by a comparator, and it will be compared with an adjustable voltage reference, and the action will be taken depending on whether one is higher than the other, whether the junction voltage is higher than the reference or the reference is higher than the junction. And then the output relay, which is a 12-volt relay, will either start or stop the fan. Now, like everything else in designing, there must be some level of consideration when you're looking to put together a design. And for the absorber, a few things went into the design. However, in the absence of my concept drawing, which I must apologize for, I will refer to the unit itself when I'm explaining some of these design considerations. One of them is the arrangement of the absorber plates. The absorber plates, for me to get what I'll say, high performance, or for me to capitalize on the heat and the available heat from the sun, the absorber plates are arranged in what I call a sawtooth fashion that will increase the contact area. So can you just imagine a tall piece of metal being squished up and it forms this sawtooth pattern. It doubles, in effect, it doubles the contact area for the absorber plates. In addition to that, there are just for those who can see, there's two manifolds that was created as deliberately. One for the exhaust, the outlet, and one for the inlet. This inlet manifold has holes that are strategically placed that will allow air to pass, not just over one area, but over both sides. So on the sawtooth side, air is passing on the top, and air is passing on the bottom. So that improves the performance even more. Other considerations were using a fan instead of being passive with the circulation. And that allows for smooth transfer of air across the plate, smooth and consistent. In addition to that, I tried to seal and prevent bypass of air internally and externally. So there was a lot of sealing and airtight deliberate actions to prevent any kind of leakage of air. And of course, we looked at using black paint, because as we know, flat black likes heat. So those are some of the considerations. On the electronic control side, temperature control side, some of the considerations were choosing materials that were robust and that were cheap and readily available. And some of those components included the LM324 operation amplifier, which is very cheap, readily available, very robust for persons like me who are not very nice with electronic equipment. The LM7805, another cheap and readily available voltage regulator. And the sensors that were chosen were thermistors, negative temperature control thermistors, 10K, which was also easy to get. And of course, I used a circuit with some modification that was proven to work and to be very effective at doing their job, at doing the job of being a comparator. So let's have a closer look now at the circuit itself. We can start at the input here, which is J2. And this is the barrel jack here that I would plug in a UL approved 12 volt wall adapter that would go send power to the inboard, and when I say inboard I mean the in-room negative temperature thermistor, after which a sensor, this outdoor sensor will be connected across here, and that will complete the voltage divider between the room sensor and the outdoor sensor, and this will now go into pin 5 of the LM324A, the non-inverting input. On the first operating amplifier, this is pretty much, you have a straight negative feedback, so this just behaves as a voltage follower. And whatever the input is at 5 comes out at number 7. It passes through R1, which limits the current as it goes into the non-inverting input, number 10 for U1C, which performs the comparator role. Now what it will do, it will look at the voltage at point A, at point 10, pin 10, which should pretty much be what it is at the junction voltage. And it will compare it with a reference voltage here. And the reference voltage is usually set at about 2.5 volts, somewhere around there. It's adjustable, and you can do that depending on how much heat you want to extract from the air. But we can talk more about that later. If the voltage here on the inverting pin is higher than the non-inverting pin, then this amplifier will switch towards a negative rail, which means that it will output 0 volts. That 0 volts, whatever voltage is outputted here, is another follower here, and it will go to the LED through R6, which is a current limiting resistor. The LED will either light or not. Then it will go to a relay that would operate and either cause the fan to start or to stop. It either sends current here or it doesn't, depending on the output from pin 14 here on U1D. Voltage reference uses 5 volts, positive 5. Also, the sensors use a positive 5 volts, which is supplied by U2, the 7905 linear voltage regulator. That gets 12 volts from the main supply, and it converts it into 5 volts, which is used by, as I said before, these two main components: the sensor voltage divider and the reference voltage divider. So that pretty much sums up what happens on the electronic side. Now, like everything else, there has to be some testing. The proof of the pudding is in the eating. And 2 tests were done: the efficiency test and the heat output test. The heat output test simply looks at the heat, the temperature of the surrounding air and the temperature of the air that's coming out of the unit. And that delta T is used in conjunction with the specific heat of air, you see here, and the mass flow rate to determine how much heat is being produced by the heater. Efficiency in this case, in my case, looks at how effective the heater is in converting the solar irradiance, and that is really a measure of how much solar energy is getting per cubic meter into heat. So this calculation that was used to, as our heat is now used, we'll now compare it with the solar irradiation to see how efficient the unit was in converting that energy. A point to note before I go on is there was challenges in doing some of these measurements, and one was the fact that I never had a mass flow meter, so I had a choice. Mr. Metcalf suggested something which I will try someday, Mr. Metcalf, but I didn't do it for this one. I just used the rated value that I got from the data sheet of 51 CFM for my mass flow rate. I converted it into kilograms per second, but there was a suggestion that I could use the fan to fill up a bag and time how long it took. Yeah, I'll try that some other day, some other time, and compare it with what I'm getting from the data sheet. But for this test, I use the data sheet information. And also the pyranometer that I got to measure the solar radiance, there was a struggle for me there. 2 things. It was a steep learning curve with the pyranometer, because I've never used one before, and it's not a very popular, it's not a regularly used instrument. And the other struggle was when I went online and I checked, the pyrometer was out of calibration for I think 2 or 3 years now. So the choice was, do I use solar isolation values that I can get from red screen, or do I use a pyrometer? Just take it as pyrometer, because I always have a problem pronouncing that word. So I opted to use the pyrometer readings, despite the challenge of being out of calibration, and and the fact that it's a steep learning curve for me, because it gives on-site reading. Red screen is really projected, it cannot really, I don't think even with an out of calibration parameter, it still works out better for me. So I opted to use it. And these are the results that I got. The delta T, the test was done over a 3-hour period, collecting every 30 minutes after the first hour. And I got delta T ranging, averaging about 14, thereabouts. The mass flow rate I used consistently throughout. And the heat produced in watts are represented in this column. I use one isolation irradiance value, for the entire project, for the entire test, And I saw where, in the end, I was averaging about 55% efficiency, and the heat output was about, as this slide says, 275 watts, or 30 watts per square foot of my instrument. How does it compare with commercial heaters? Not very well, but I was getting some heat out of it, and I figured there were some challenges, especially with leaks, because there was a number of leaks, especially internal leaks. So I realized that, there were problems there. So in all, summing up the entire journey, the entire experience, it was an interesting journey. And at the end of it, I can say that I made a solar heater. It has some challenges. I have some challenges because as it is now, it is not fully functional. The temperature control side of it is not functioning as it should. In the end, I found it to be that the operating amplifier was at fault. There was no time for me to replace it. I had no replacement at the time because I pretty much damaged the 3 that I bought between the first prototype and this test. So from that point of view, it was a little bit disheartening that I didn't have full functionality, but I can report that the unit can produce heat and can perform as designed, except for the fact that it will not shut on and off depending on indoor and outdoor temperature. Limitations. There are always limitations with everything. With this, solar energy is only available at certain times. So to overcome that, you have to look at how we can store energy, how for use in times when things are getting, cold or dark. So the total cost ended up being $322.61, which is a little higher than budget, but it was worth the try, it was worth the journey, and I thank you all for staying here with me. Thank you, Mr. Metcalf, for your help, Mr. Legier, and all other fellow students for your help and for your consideration and patience over the 6 months. That is my project. Thank you for your time. And now for the demonstration. Yeah. All right, so we have a little artificial sun here. That's Mr. Legier's son, actually. Mr. Legier's son.
My son.
S-U-N.
Should be daycare.
Not S-O-N, S-U-N. All right, so I have here that we keep our eyes on. Yeah. Let's keep your eyes peeled on the probe. I have two sensors, two thermocouple sensors installed, T1 and T2. One will go on the outlet of the heater, and the other one will stay in the room. Alright. Let me just get some power on. Right.
Yeah.
Can you actually see this?
It's upside down. Turn the camera.
I may have to turn it.
Yeah. George, just rotate the camera when you use it. Yeah.
All right. You know what? I'll just hold it here. All right, so can you focus? Just put that. Yeah.
If you let it before.
No, just wrap it so it can hold on to the probe. Yeah, so you don't have to hold it. I don't want anyone to think that you are the one rubbing the hand. So just let it loose. That's it. Okay, so now this is set at T1, and T1 is the room. That's the room temperature. T2 is the outlet temperature from my heater, and this will give you the differential, T1 and T2. Alright, yeah, that's it. So as it is now, we are having a 3-degree and rising temperature difference between inlet and outlet. And once we achieve steady state, which takes a while, it takes, you know, maybe a 5 or 10 minutes, you will see more significant temperature increase.
You could let it heat while we ask questions, and then we can come back to it.
All right, sure.
That works.
Go right there.
Where do you want to go first? You can ask questions.
You had mentioned during your presentation that flat black paint likes heat. Does any flat black paint work for this application?
Any?
Yeah, any kind of flat black paint.
Any kind would work, but there are some that works better than some. With high emissive, with a high emissive.
Maybe I just wanted you to repeat that.
As long as you get the first two syllables,
right?
you know what you're talking about.
Yeah, I can spell it, you know.
I can spell it, yeah.
Yeah, those are the better types to be used. In fact, I did do some. I did it with a different paint before, and I'm getting much better with this IE. Let's call it E, the IE paint. I'm getting much better results. So the theory is true. It's not just any paint. Any paint will, flat paint, flat black paint will work, but there are some that work better than others.
Can you bring up your schematic?
Sure.
What's the purpose of C2? You might want to enlarge it.
Yeah, switch to presenter view so we can see it.
How do you?
Shift F5 will do it.
Shift F5?
Yeah.
Thank you.
You're welcome.
But there's no F here.
That's F5, not 5, right?
Yeah, just
Shift 5 deletes your whole presentation.
Right here. That almost happened. I've not seen F5.
On the top row.
Just look on.
The top row of keys on the keyboard.
Just start the presentation and then just like start.
I got it. Shift F5. Yeah, I'm seeing that now.
Yeah. And in a minute it'll come up.
You know what? Forget about it.
Oh, that was the delete key. No,
Oh.
no, it's
Forget
coming.
mine.
There, no, there it is. There it is.
Yeah. Yeah.
So yeah, what's the purpose of C2?
Okay, C2 will actually be like a filter for the, especially for the U2.
to filter what?
Yeah. Filter any ripple that may be coming from. For one, as well as if there's any switching, because whenever that relay switches, there may be voltage fluctuations, so that capacitance
You're
is.
confusing C2 for C3.
Pardon me?
I think you're confusing C2 for C3.
No, it's on the input side.
Yeah.
If looking at J2, I'm connected on J2, and that will go to a switch. When I close that switch and send power to the fan, it can cause the input, it can cause some kind of a fluctuation.
That's not why C2 is there. C2's got a really specific reason for being there. It has to do with whatever's on the other side of J2.
J2 or J3?
J2. Your 12 volt DC in.
I didn't get that. So.
Your 12 volt DC in jack. I think it's J2.
Yeah.
What could be? What's on the other side of that?
What? On the other side of J2?
Yeah.
Oh, that's the adapter.
Okay. So is the adapter?
Well,
Right
it's a lot of line with inductance and all of that.
The
So
adapter may not be right there, right? It could be very long.
yeah, it could be long.
So what's the inductance going to do?
Well, it would. When I'm thinking more about it now, maybe C2 is more of a.
Let's forget C2 for a second, okay? Let's just imagine there's a big inductor there in series with your high power supply, okay? And U2 all of a sudden has a large demand on it current-wise. So what's the purpose of U2? If on the output there's a large demand on it current-wise, what's the purpose of U2? What's its main purpose?
Main purpose is to maintain a steady 5 volts.
Steady 5 volts,
Right.
and therefore if there's a large demand of current, what's if U2 wasn't there, what would happen with the voltage across that line?
It possibly would drop out.
It would-
Maybe to get that
it would
low
drop,
that it would
right?
drop out.
It would
Yeah.
drop. So therefore the regulator has to supply that large amount of current. Okay? The voltage starts dropping. There's a feedback. What does it do?
It adjusts.
It adjusts, so it raises the voltage.
Right.
Right? Well, for it to raise the voltage means what at the input of pin 1 of U2?
If it's raising the voltage, then
what do you think has to happen at pin 1 of U2? If it needs to raise the voltage at the output,
then it needs more.
it needs more what?
Voltage, current, sorry, current.
Current.
Yeah.
Well, we have an inductor in series of that, a very large inductor. What does a large inductor try to do?
Takes current.
Hmm?
Likes current.
Likes current? Like a gate or something?
No.
What is it?
No, it would want current, yeah.
No, well, it may not, but what does it try to do to current? When current changes, what does the inductor try to do?
Continues.
Well, it tries to maintain its original
It continues in its open
So if
state.
we have a little bit of current, and also we have a high demand of current, what does it try to do?
It goes high.
No, it tries to prevent it. Right? It
Yes.
tries to prevent change in current,
Mm-hmm.
right? Okay? So if it tries to prevent change in current, okay, let's say that's gonna happen, right? If it tries to prevent change in current, will U2 be able to do its job?
No.
No. That's right. No.
So it's for stability.
Hold on. So if the problem is there's a large amount of inductive reactance going on, how do I make that inductive reactance disappear?
Add some capacitance.
Because if I put capacitive reactance, what happens?
Yeah,
It offsets.
Yes, it offsets that inductive.
It acts like a charge bucket.
Yeah,
It can
like
supply
a tank. Yeah.
the extra charge for the current.
Right.
So it permits U2 to do its job.
Yeah.
Okay?
So
If
it's
you
really-
go look in the data sheets for that regulator, it will tell you, if you have a very long line prior to that, if your power supply is very far away, you need to make U2, you need to add C2 to that. And it also says something else about C2. What about its physical location?
Close to the regulator as
As
possible.
close to the regulator as possible. Why?
Well, the farther it is the more inductance it will be exposed to.
Anything after the capacitor is inductive, right?
Yeah,
So-
but also the tracks are inductive as well.
Right, so it'll be less effective on that, right?
Yeah.
So what does it look like in your diagram? It looks like there's a long inductance, doesn't it, between C2 and the input of the regulator?
No, that's just for the drawing sake, but physically on the board they are as close
But
together.
probably
as
it
possible.
should have been located right next to pin 1 and then tied to the ground terminal at the inductor, right?
Typically on schematics,
Yeah.
although we usually say on schematic, the physical location of components don't really represent physical location
Yeah.
in real life. But when things like capacitors like that have to be close to something, we usually do position.
Right,
them.
right.
Same thing like decoupling caps, we often put them right near the BCC pins for the same reason.
Yeah, point taken.
If I'm looking at it too, C2 doesn't seem like it is linked with the regulator. It should be right next to it.
Yeah.
Yeah.
that's what we're talking about.
Yeah.
Yeah, that's what the point he was making. Even though on the board it physically is, but on the schematic, because of the importance of it, I should have had it being represented as such.
Any other questions on this?
Oh, I do have one.
Yeah, go ahead.
That first amplifier you have, what is it? It's U, is it U?
Yeah,
You want
you
C?
want- you want
Yeah.
C.
Yeah. Why do you have that?
Why do I have what?
That regulator, that amplifier there.
As I said before in the presentation, it's really a voltage follower. It's unity amplifier. It's there to separate
What is
the
that?
impedance between the all right, the voltage the voltage divider on the voltage divider between
It
here.
has a specific job, like the voltage follower you had there. It has a specific job.
Yes, it's
What is
there to ensure that whatever the input, the non-inverted input on 5 goes to 7. It's unity. It doesn't, it's because of negative feedback, what goes into the non-inverting comes back out.
I know it's unity, but why you have it there?
So why wouldn't you just take it out?
Yeah.
Because it's gonna
That's
be
the point I was trying to make. On that side here, there's high impedance. Right? And on the other side is low, the impedance. So you want to have like a separation between them because they will behave as, in itself, it will behave as a voltage divider and it will cause instability on my signal.
So at the input side, you would have high impedance, and
Yes.
at the output side, you
How
would
much
have.
impedance would you have on the input?
Yeah.
The input, it would be the 2 voltage, the 2 sensors, which is 10K.
Okay, so 10K
10
each.
Ks.
Then how much impedance do you have on the other side?
That would be 6 point. That was 6.8K.
Okay, so it's looking pretty similar. It's a way
It's
same
not
scale.
That's not the impedance you're looking for. What's the impedance of the amplifier itself?
Yes, amplifying impedance.
And what is it? What's the operation? of the
I
amplifier?
don't know.
And you do it again later, right? You have another voltage follower after, right?
Yes, and for that same purpose.
Just, if you look at the input, right, you have 2 resistive elements there, right? Temperature sensitive resistive elements.
Yeah,
They're configured as what?
voltage divider.
Okay. So your purpose is to keep a certain voltage between them.
Yeah.
Okay. What happens if we get rid of all of everything that's to the right of that, okay? And we start putting a resistor in there that's similar to the 10K values. What's going to happen to your voltage divider?
All right, let me try and understand what you're saying. If I get rid of all the sensors,
That's everything, all the op amps now, let's just get rid of all that. Let's put let's put a 5K resistor in the ground.
oh, so I'd have a voltage divider with the 2 sensors connected to a 5K.
K to ground.
To ground, yeah.
Are you going to have the same voltage across the voltage divider? No, is it going to be higher or lower?
No.
With reference to whatever. The ground. It's going to be lower, right?
It will be because some will go, yeah.
There's one of the 10K is going to be in parallel with 5K.
Right.
Okay. Now let's say that 5K varies because of circuit operation. That means that the voltage between those 2 resistors is going to vary depending on circuit operation, right?
That's true. That's true.
Okay. So we don't want that because that's going to be misleading, right?
Right. So that's why.
If you put a buffer in between, what does the buffer do?
It separates. It would separate.
How does it separate?
The voltage divider will be on one side though. As
Yeah,
opposed
it's true, but what does the voltage divider see as impedance?
It would not see it. And it,
It'll see whatever that pin is. What's the non-inverting pin on the buffer amp there? I can't see it from here there, but
yeah, it's 5.
Pin 5. What's the input impedance there?
It would be where the voltage divider meets.
No, that pin 5. If I look into it, what input impedance will I see? Will it be very low or very high?
I'm thinking. They would be on the high side.
Very high. How much high?
Very high.
So how much is very high?
Infinite.
Well, I don't think it's infinite, but in the tens of meg at least, right?
It would be very high.
Okay. So then, will it be loading down your voltage line?
If the impedance is high?
Very high. Will it load down your voltage line?
No.
No. So that's how it isolates. Because now, no matter what happens on the other side, operationally,
it will not affect that.
All it sees is a very, very high impedance.
Because of the very high impedance. I get you. I get you.
And so why do we do it again on the other side?
Yeah.
It's, as you said, you mean on this side? No. Let me get back to this.
You have another buffer.
Yeah. This buffer.
Yeah. So why do we do it again there?
All right. I'm looking here. The impedance here would be low. Coming out of here. And the impedance on this side, I think it will be higher.
Will it be stable? Ask yourself if it will be stable.
I didn't get that.
Will it be stable?
If what will be stable?
The output. On the output side, will that voltage tend to be stable?
By design, yes.
Really? When that coil turns on and off and on and off there, that's going to be stable?
No. From that point of view, no. There will be still this a little bit of fluctuation here.
Yeah. So if that fluctuation was happening, it was springing back into the feedback, or not the feedback, the positive feedback of the comparator with hysteresis there that you had. Do you think it would affect that?
If it's feeding back this way?
Yeah, there's no buffer there. Let's get rid of the buffer.
Okay.
So that there's a lot of variation in current there now, right?
Yeah, it would affect the...
Do you think it would affect that?
It would definitely affect the the comparator.
So how do you isolate that from the rest of the circuit?
What do you mean, guy?
Yeah, because what does that part of the circuit see now? The triggered comparator there. U1 or 2.
What? This one E?
No, the other one.
U1C.
U1C. So
yeah.
Your schematic is very small.
Yeah.
So U1C, what does it now see for impedance at the output?
It sees this. A high impedance here.
Just a high impedance?
Yeah, high.
Just a high impedance?
Very high.
Very high. So what does that do? So what does it do?
Yeah, it causes, well, because it's high here, then it will...
It will always see the same thing, right?
Yeah.
So you're isolating, again, a very variable part of your circuit, the output,
from a very high part. Yeah.
So now that we're at a time for questions, show us the last part of the demonstration. Let's see.
Yeah, with Mr. Litcher's son, I'm up to 5.2.
Oh, look at that, that's great.
Yeah.
My son does a great job.
Yeah.
Something to be proud of.
Good vibes.
I feel much warmer now. Thank you.
Oh, yeah. I'm glad I could help.
Yeah.
Stand on the word.
And does it feel that
Good job, George. Sorry, may I ask you a question?
That's all right.
Come on, you were going the right way and then you changed. You're going to say about the leaders and then you change.
One reason to not go last.
Okay, why are you leaving from
You're gonna set up now? Oh, make sure you get in.
Yeah.
Thank you, Jan. You're gonna make it here. He's gonna make, yeah, okay, good.
No, he would have been good. In fact,
You're gonna skip all those meetings, are you? Oh, they're online meetings, yeah.
Yeah, it's a different.
And then I was like, well, we can continue.
Are you a teacher that goes? I gotta go do it. I got a bunch of Bangladesh in front of that. Brenda.
You should practice.
We won't expect to see her.
No, but I gotta go parse through that. There's a bunch of companies like down small. I was like, oh, yeah, it would be very low. 9 hours. Not just there. 9 hours.
How do you find it going?
I can see people that retired or
First thing you're
moved on earlier than they would have, and now realize. I don't hear
So that's a good.
I think it was like
I don't know. If you just click, if you click without
For you to walk with that,
or you can do that.
So there's a bunch of cameras on
Do you have the muscle lifters?
I think I'll take it on tomorrow. I'm going to leave that to the entire.
Okay, then should put it on the side.
Yeah.
We need to take this back.
Yeah. Take all of this. I'll hold it. These are.
If you improve your presentation,
and beyond that,
F5 starts from the first slide.
so you're no
When
longer
you're all
like,
done, you know, when you end up with the last slide, when you're all done, you just exit for the interview. That'll adjust, okay, a couple seconds later, when you switch to the camera.
yeah, now it's everything's removable.
As it is. Now what I should do is put presentations in here.
Actually, like, that.
Use presenter review, yeah.
Here they push these through the valves, and it works all right. If you have anybody in the class that's new,
Yeah, if there's interviews that would.
Oh, yeah, we have those cameras.
You got your-
Every single time a car drives by, it'll go there and it's like,
when I'm a pacer, and it'll go over, and you have to. You gotta get used to it. I don't particularly like them.
they have those at the conference rooms, there'll be like a floor.
Yeah, we got the Cisco setup there.
And then like it'll like box right on your
I
face.
cannot read
And
it.
somebody says something
I was
over
able to
here,
read
like
it, but
whisper
I don't have the
it,
permissions.
it'll pop out again. Or they'll pick up a car outside, or I don't know, somebody walking outside, bitches, like.
Well, this one here, we can turn off the
Go in that way.
Topic, and then I.